Yeah, so now we are ready to proceed to our next talk. So our next speaker is Sungjin An. So I can already see your screen, Sungjin. So let me give you a short introduction first. So Sungjin is an associate professor in the School of Computing at KAIST, where he leads the Agent Machine Learning Lab. His research interest is to develop machine learning algorithms for perception, cognition, and action in order to make a human-like intelligent agent. In pursuing this, he is particularly interested in learning representations and models of the world and the policies in a self-supervised and structured way with the tool of deep learning, reinforcement learning, and probabilistic learning. And Sungjin will be talking to us about his amazing works on toward structure slots. Take it, Sungjin.
All right. Thank you for the introduction. Yes. Today I'm gonna talk about this title, toward the structured slot. So I want to first start. Start by understanding what current representation system is doing in terms of this System 1 and System 2 framework, which is proposed by Daniel Kahneman. So System 1 is like the what current deep learning is doing very well. We perceive the scene and we immediately know what's the object or kind of segmentation, things like that. This doesn't require the intended like effortful reasoning process, but System 2 is different. System 2 is like reasoning, planning, causal inference, or explainability, or it also requires systematic generalization. What is common in System 2 abilities is to manipulate some knowledge pieces. If you think about reasoning or mathematical reasoning, we should be able to identify some tokens or knowledge pieces, and we should be able to deal with this knowledge pieces. However, current deep learning is not doing this thing very well, and the one important question what this object-centered learning try to deal with is how can we get this knowledge pieces usually from this visual input. So in this talk, I'm interested in discussing about this unsupervised object-centered representation learning. And this unsupervised object-centered representation learning is mostly about learning general representation framework for learning composable and modular and reusable knowledge pieces from this visual scene. So on the left-hand side of the slide, we have the typical representation system, which we usually represent a scene by a single vector. However, in this object-centric learning, we want to learn these knowledge pieces so that each object is corresponds to some vectors dedicated to that object. So in learning this kind of object-centered representation, there are two major challenges. So the first challenge is to achieve binding, which is basically about how to group relevant features together. And another problem is structuring, which is about how to make the representation more informative within this bounded representation, for example, like achieving disentanglement. So in the figure below, if we are given like image of apple and pear, we can represent its features like a green apple or yellow pear. But if we are given an image which contains both of these objects, apple and pear, without proper binding, the representation may not represent the scene properly, because we don't know which one corresponds to red or green or apple or pear. So if we can do binding correctly, then we'll probably have the representations, something like shown on the right-hand side. So that's about binding problem, and structuring is something like disentanglement, whether within this representation assigned to one object, can we provide a very informative representation that will be useful for the downstream layers or tasks. So slot attention is kind of one of the most popular approaches in achieving this. So this is a deterministic mechanism for binding. So it applies comparative spatial attention on the images, and multiple slots draw information from these local areas that is corresponding to an object. And then from this slot, it tries to decode object-centric images. And then finally, the full image is reconstructed by combining these object-centric reconstructions. So that's the typical approach in most of the previous works have used. But this has two main challenges, which I want to talk about, how we can improve it. So the first challenge is how to make it work on complex natural images. So most of the object-centric representation learning in the past have dealt with, usually applied to simple images like some monotone objects. The reason is because this is a very challenging problem, first of all. So learning object concept without using any objects-wise label is a pretty challenging problem. So it's been researched for the past like 5 years, and then there have been many impressive progresses in this line of research, but we are not yet there where we can apply this approach for natural images. But the field is moving fast toward that direction, and today I'm going to talk about our effort in that direction. And the second problem is how can we obtain more informative structure within a slot. So in slot attention, which I showed in the previous slide, it doesn't provide, even if we structure the scene as a set of slot representations, it does not provide a good structure within slot. And in this talk, the second part of the talk, I'm going to talk about how we can provide better structure for the slot. So the first topic content is about our paper about slate, which is a slot decoding transformer. So the first question is why it does not work well on complex scenes? I mean, why previous object-centric approaches or most recent ones are not working on complex natural scenes? So most of the unsupervised object-centric learning models use this specific type of decoder, which I call object-centric mixture decoders. This mixture decoders has this form. First, it has the object-centric representations, one vector assigned per object, and each object representation is decoded using object-centric decoder. So from this object-centric decoder per object, we usually generate object-wise masking and also object-wise image. And then finally, the final image is constructed by combining this masking and object images. So this is the typical approach most of the object-centric representation learning works have used in the past. But this approach, this approach has two issues, which basically preventing it from applying to complex images. That's our investigation analysis. So the first issue is the capacity dilemma, and the second issue is the pixel independence. So I'm going to explain about this one by one. So the capacity dilemma is about, basically it says that it cannot use complex flexible decoder. So the reason is if you try to use complex flexible decoder as a object-centric decoder, this complex decoder try to explain the whole image instead of just capturing one specific object and then try to reconstruct that object. Because it's too flexible, it try to capture the whole image. I call this problem as a slot degeneration. So if you use usually in this decoder, strong decoder, then slot degeneration happens, then object emergence fails. Cannot make assign object to each slot. So that's why most of this mixture decoder the kind of weak decoder, like spatial broadcasting network. So by assigning intentionally, by using intentionally weak decoder, we can handle slot, we can resolve the slot degeneration problem. So with this weak decoder, object emergence will become easier. But the problem is that it cannot now handle complex images because the decoder capacity is too limited. So usually this weak decoder can detect object using color bias. That's the problem of the capacity dilemma. And the second problem is the independence dilemma. So the problem is like this. So on the right-hand side of the figure, we have the typical mixture-based approach. So in the input, we have the pixels, and then we apply slot attention across the pixels. So in this phase, which I call pre-slot interaction phase, we can model interaction among the pixels. So when we obtain slots, the slot is after analyzing the interaction between the pixels. So that's fine. But after obtaining the slots, we use this pixel mixture decoder, which does not apply any interaction modeling, because from each slot, it independently generates pixels and masking. And then eventually what is generated, the pixel is just weighted sum of these pixels and following the masking. So this means two things, two limitations. It does not care about other pixels generated in other area of the image, which provides should provide important context information. And it also does not aware of other slots, what kind of information other slots are containing and how it is contributing in generating the image. So, so in short, in the decoding process, everything is completely independent. So that significantly limits the capacity of the decoder. So based on this analysis, we see that the existing mixture decoder has these two problems, capacity dilemma and pixel independence problem. And because of this capacity dilemma, traditionally, people have thought that a transformer decoder is not a good choice for object-centric learning. But based on this analysis, we hypothesize that we can use transformer decoder. They can model complex scenes. And it would probably not make this slot degeneration problem because of the slot bottleneck provided by slot attention. So based on this observation, we designed this architecture called the slot attention transformer. And the idea is basically to introduce this autoregressive transformer decoder on top of slot attention. So by doing that, we turn the problem from set to image generation. We change the problem to set to sequence generation problem. And then the image just becomes as a sequence of the image tokens. So as you can see here on the right-hand side, because of the transformer decoder, now when we generate a pixel, it can see every context pixels, unlike the pixel mixture decoder. It knows what has been generated so far. And also, we condition the transformer on the generated slot. So in addition, it can also see what other slots are containing, what kind of information. So this way, generating a pixel becomes much more complex model that can see other pixels and other slots. So if you can represent the process as a model, it's like this. So here we have all the past pixels X before the index I, and also all slots from slot 1 to slot K. So conditioning on that, we apply transformer and then we generate a pixel from there. So by applying this simple change, this is basically introducing transformer decoder, we surprisingly observe very impressive performance improvement. So what you can see here, this is like a textured MNIST data set. As you can see here, the original image background contains complex texture, and also foreground digits contains complex texture. So sometimes it is even difficult to identify the object by humans, like the first figure and then the third row figure. And by applying slate model, interestingly, we can see that the model can identify the foreground object and then also have some slots for other areas. Interestingly, like this case, the third row, this digit is very difficult to identify the digit, even to humans, but the model, we can see that the model can identify the object. On the contrary, on the right-hand side, this is the slow attention model, which uses mixture decoder. It cannot identify the object properly, like in this example. And also, the traditional mixture decoder-based models suffers from strong color bias. So the way it works is because the decoder is too weak, it usually try to group the same color as one object. So as you can see here in this example, here in the image, the woman's hair and background are all black color, and then we can see that the slow attention approach try to group this hair and background as one object, even if semantically they have to be treated as a different object, and also the skin color becomes an object. But in Slate, interestingly, it can do some to some extent like this kind of a semantic object segmentation. So here the hair is separated as a separate object, even if the background is the same color tone, and also face and neck is separated as a different area, even if they share a similar skin color. So this is interesting observation. And another way we can see this is also, we can see this model as a kind of illiterate DALL-E model. So DALL-E take the word as input, and then it can generate image, which is unseen before, like some interesting composition ability. So because we have pretty similar architecture, instead of using input word embeddings, we obtain visual word from this Slate encoder. So we did some experiment clustering this slot representation, and then use that cluster the slot as the visual word to generate new images. As you can see here, we use this Bitmoji data set on the top row. And then here, these are the learned visual clusters, which corresponds to different types of eyes and faces and hairstyles. And then we can see this model can do zero-shot compositionality. Here we picked arbitrary visual words corresponding to different face type and hair type, things like that. And then our model can compose unseen combination of the visual words and then generate realistic face images that is similar to original image. But the slow attention with mixture cannot do this, cannot have this ability. And also we did a similar experiment, and this is typical like male space, and then we applied some long hairs, and then in the data set there is no this type of images at all, but the model can still generalize and do out of distribution compositionality ability. So interestingly, this is maybe shown or much simpler than what is shown these days using this language and visual language models. But interesting part is this model, we don't use any language. This is purely done only from the images. And then excited by this advance, we try to improve this model to video. The main question, how can we take advantage of the temporal information to improve Slate? So traditionally, I think people have used this kind of image, but the question is how can we deal with this kind of naturalistic videos? And this model, Steve, is the first model that actually can achieve good unsupervised object-centric learning for this video. So the architecture is pretty simple. We only use reconstruction objective. We don't use any object-centric objectives. And then the encoder and decoder of the network is simply slate encoder and slate decoder. And in the middle, we introduce slot RNN to model the interaction of the slots, temporal interaction, and then, to model the temporal interaction of the slots. And as you can see here, this simple model can show pretty impressive performance upgrade compared to the previous models like ECCV or OP3, and especially when they think this MobiText dataset contains very complex texture. And for that case, we can see very significant improvement compared to other methods. So this is some result. So this is the dataset we made MobiText dataset. And this contains very complex textured object. And interestingly, our model can identify object really well. And while the previous method failed completely. And also this is another data set, cater tags. We see similar performance. And also this is the movie data set where the camera moves, and also the scene is much more naturalistic. And we can our model can handle this scene without any supervision. And other examples of movie we can see the SEBI model fails here, while Steve works pretty well. And also we applied to actual natural video taken from YouTube. So on the left-hand side, we have this traffic data set, and the model can handle it pretty well. And on the right-hand side, we also have the aquarium data set, and the model can identify the fishes pretty well. And finally, we also applied this model for object-centered reinforcement learning. We pre-trained this causal world task where object try to move some object. And then after pre-training this video using Slate, we applied RL, and we can see this object-centric reinforcement learning achieves the best performance here. And yeah, that's about how we could handle, or how we can make object-centric learning to handle more complex images or more naturalistic images. And then I want to move to the second part where we want to give more informative structure for the inside the slot. So about what would be a good slot representation or object-centric representation, I want to introduce this three desiderata for improving unsupervised object-centric learning. The first one is within slot disentanglement. So the slot representation can split slots, but within slot, it does not provide this disentanglement. And also, by disentangling within slot, we want to represent each property as a vector, not as a single dimension variable. And also we want this learning system or learning process to be deterministic mechanism, which can be more broadly used as just like a drop-in or plug-in module in any arbitrary neural networks. So previous slot representations, we can analyze in this way. So the iodine, which provide disentanglement, but this disentanglement is not vector property level. Disentanglement is like VA, so where each dimension of the representation try to be disentangled. And this is also VA, because it's VA-based framework, it's not deterministic mechanism, it's a somewhat more complex probabilistic model. And the decoder is also mixture decoder, so it inherits the limitations of the mixture decoder. Slot attention, yeah, it does not provide disentanglement, but it's a deterministic mechanism. And Slate provide transformer-based decoder. So eventually what we want is we want disentanglement, and we want to represent the property as a vector instead of a single variable. And also we want it to be deterministic mechanism, and we want to use transformer decoder. So we introduced to achieve this the block slot representation. So ideally, the block slot representation will represent a scene like this. So on the left-hand side, the slot attention represent the scene. If it is containing 3 objects, it will assign 3 slots, and each slot contains the information about the object, but it will be entangled. But ideally, the scene can be represented like this. We have 3 slots still because there are 3 objects, but inside the slot, we will have disentangled properties like color and shape and position of that object fully in a form that is fully disentangled. So we call these as blocks, and this set of blocks compose a slot. So now I'm gonna, and importantly, yeah, we don't want to provide any label here again. This is fully unsupervised, and this concept of block should be emerged by just observing the scene. And also, one reason why we want vector-based property representation, it is to encourage this transformer compatibility. So one of the reasons we want to use slots is because we can use transformer for implement more high-level reasoning process abilities. So on the left-hand side, this is traditional all-in-one vector like VA that represent the whole scene by a single vector where we cannot use transformer. But by representing a scene by slot, a set of slots, and now we can apply transformer, and then it can model the interaction between the slots. But within slot interaction or between slot property interaction became difficult. Eventually, if we can achieve this block level block slot representation, then we can achieve this block level interaction model, which is more flexible, should be more flexible than slot representations. So how to achieve this? How to learn the blocks? This is our approach. So we, given a scene image, we apply slot attention, and then the slot attention, we obtain 1 slot. And then we break this slot into a set of sub-slots, so which we call blocks. So we break the slot, split the slot, and then we obtain block. And then that block is given to this block module. And then a block module is similar to slot attention is an RNN. So for some iterations, like 3 iterations, it updates each block representation. And then the block representation is recomposed at the end. And then that is again given to the slot attention. And we repeat this process a few times. And then finally, the final blocks are, the recomposed blocks are given to the next layer. Then we want each block represent the independent properties like color, shape, and position. So this is encouraged because these blocks are fully independent RNNs. And this is for one object. This is for object 1. And object 2, we have the same break, update, and recomposition iteration. And then for another object, we have the same process. So eventually, we provide these blocks as the output to the next layer. And also, we introduced this concept memory sharing to encourage this independent block learning. So where this concept memory is shared. So for block 1, we have block 1 concept memory that is shared the block 1 of different slots. So by sharing this memory concept memories, every block should use the same language that is contained in this concept memory, and that encourages also achieving more clear disentanglement of the concept here. And lastly, we also introduced this concept of block binding. So block binding is required because from the perspective of downstream layer, it doesn't know whether this blocks belongs to which object. So to encourage that, we introduce just one single layer of transformer so that these blocks of belonging to the same object to communicate, and then they became aware of each other. So from the downstream task can know that, okay, these are the blocks, but they are also belonging to the same object. That information can be encoded in the representation. And then we evaluate this approach, the block slots. We use this DCI metric, disentanglement, completeness, and informative. And also we measure the segmentation quality using FGARI. And we use this 3 data sets, Clever Easy, Clever Hard, and Clever Text, which contains different difficulty or different levels of variabilities. So yeah, as you can see here, the block slot attention outperforms the slot attention and iodine in all metrics, which is actually achieved pretty big significant improvement. And in terms of FGRI, all 3 methods works similarly, but the disentanglement and completeness and informativeness, our model performs much better. And we did some emulation study as well, and it turned out that all components are necessary. Here, the components we test is the concept library and the block binding and the RNNs, the shared RNN and not sharing the RNNs. So as you can see here, if we remove this component, the performance is degrading. So it turned out that these components are necessary. And we cluster these blocks to see then whether these blocks are really containing or mapped to some independent concept. So as we can see here, for Clever Text dataset, the block 6 are all representing different shapes, and block 1 represent different materials, and block 4 represent different positions. So this disentanglement is working pretty well. And for Clever Easy dataset, similar thing is we can see the similar result. So using this result, we can do also concept manipulation, whether it is working as we expected. So here we did like taking an image and then encode it, and then we obtain 2 slots. And then we swap the color blocks. So originally this gray color is on the left, but it is assigned to slot 2. And also this pink color is now assigned to slot 1. And then see if this is well disentangled, and then the decoder can understand it well, then it should be able to generate image where only this concept, the color concept, is switched. So as you can see here, you can do it pretty well. And like in this case, yeah, we tested it on different instances and swapping the shape and swapping the color, swapping material, position, size. As we can see here, it works really well. So from this, we can see that this disentanglement is working pretty well. And also, finally, we can also see this idea as something like you're making visual analogy. So if we can define analogy as to find a partial similarity between 2 things, then yeah, given these 2 images, the representation represent more clearly what is the main difference between these 2 more conceptually. And this could be the base of achieving some level of visual analogy making. So the conclusion is, in this talk, I introduced 2 recent advances in object-centered representation learning. So which try to resolve the 2 major challenges. So the first challenge was how can we deal with complex scenes like natural scenes, and the second challenge was how we can give better structure within slot. So to resolve the first challenge, we introduced this model, Slate and Steve, which take a powerful transformer decoder And we showed that it became really powerful object-centered representation learning model that can handle very complex scenes. And also to give a better structure, specifically the better disentanglement structure, we introduced this concept of a block slot, and they can provide disentangled and vector-based and also deterministic mechanism to achieve this. So yeah, that's it about my talk. And thank you for
Thank you
listening
so much,
my talk.
Sanjay. Yeah, thank you so much for the nice talk. There are a lot of novel ideas and cool results. Yeah, so I see one question from the audience. So how do you generate per slot decomposition for slate? I think this is regard the first work. So how do you generate per slot decomposition if the final image is not sum of individual images?
Oh yeah, so in slate, it's just similar to you can think of maybe machine translation. So machine translation, we have source sentence and target sentence. And source sentence doesn't need to be, I mean, for example, number of words doesn't need to match to the target sentence. It is just seeing the source sentence, and then by conditioning on source sentence embeddings, it generates target sentence. So similarly, in slate, the slot became the source sentence, and in the slot, it contains information about the object. And then the decoder became the target sentence, and the decoder, by seeing each slot, it can generate each pixel tokens one by one, auto-regressively. So it doesn't need to have separate decoder per object. It just know what is there in the scene through the conditioned slot.
Okay, thank you so much, Sanjay. Yeah, I think because of the time, I think we have to move ahead to the next speaker. Yeah, thanks again, Sungjin, for the nice talk. Yeah,
Okay,
so maybe Chris, you can try to share the screen while I introduce you. Yeah, so Chris Xie is a research scientist at Meta Reality Lab in London. He received his PhD from the Paul Allen School of Computer Science and Engineering at the University of Washington. His interests span the intersection of machine learning, computer vision, and robotics. In particular, he is interested in investigating visual representations that enable robots to perform physical tasks such as object manipulation in unstructured and cluttered scenes. And yeah, I can see your screen, Chris, and go ahead talking about this segmenting and manipulating unseen objects.
Awesome. Thanks a lot, Kaitun, for the introduction. Hello, everyone. Thanks for attending the talk. I hope you're enjoying the workshop, as I am. My name is Chris, and I am a research scientist at Reality Labs in Meta. But in this talk, I'll cover some of the work that I've done as a PhD student at University of Washington. Cool. So this is for some motivation. One day, robots will be deployed ubiquitously in novel, unstructured environments like homes and offices. And hopefully we'll have robot butlers that will clean, cook, and automate the menial tasks away. But in order to intelligently operate in these environments, the robots must be able to reason about unseen objects, as it's infeasible to assume that all possible objects have been seen during a training phase, at least with today's current technologies. So when I say an unseen object, what I mean is a novel instance or an instance of a novel class, basically something completely unknown, unseen. For example, in the bottom right photo here, in order to clean this floor, this robot needs to be able to reason about like the slippers and the random toys on the floor and stuff like that, anything that could possibly be on the floor. So in these types of unstructured environments, robots need to be able to perceive the environment, plan an action to manipulate the environment, and then execute that plan in the real world. For example, perception can involve segmenting an object of interest. Planning can involve sampling a grasp pose for the segmented object, and then acting involves executing that grasp to pick up or manipulate that object in some desired fashion. And perception, obviously, here is kind of the precursor to planning and acting, and most of my work has kind of revolved in this area, so that's where it will kind of focus. All right, so in this talk, it's divided into two parts. And the first part, I'll cover a few projects that I've done that revolve around segmenting unseen objects. And in the next part of the talk, I'll mention a couple of works that involve manipulating unseen objects using the segmentations from the works on the left-hand side, and do something fun with the objects. Okay, so let's go ahead and get started with the first part of the talk. So segmenting unseen objects. The overall goal of this is stated here. For this problem, we're given a single RGBD image, so we have RGB and depth. How can a robot segment unseen objects in tabletop environments? Now, why tabletop environments? Well, we need to focus our problem to a tractable domain. And so we focus our problem to tabletop environments, which is a common testbed for many robot manipulation works. So let's, for example, say we have a Baxter robot here, and it's passively observing a scene. And let's say it sees something like this in the form of an RGBD image, and that's input. Ideally, we would get something like this at the output. So instant segmentation masks, of which then it can do whatever it wants with. So how are we going to solve this? Well, we take inspiration from previous works, a few of which we show here, and we formulate the problem as class agnostic segmentation. So what is class agnostic segmentation? Essentially, in this branch of work, all objects are classified as a single class, like just basically like a foreground object class. So when training these models effectively learn the generic concept of what an object is, and that is implicitly defined by the training set. So for example, you can take Coco instance masks, for example, and just train an object segmentation algorithm to segment whatever is in Coco, essentially, and it roughly learns what an object is, and that's defined by 80 classes in Coco. Okay, so we're going to train a model, as you know, that's what most computer vision models are these days, some kind of machine learning model. But these models need data. So where can we get such data, specifically for the domain of tabletop environments, right? And as in many robotic settings, no real world data exists for this. So we have to generate our own. So what we did was we basically took a bunch of ShapeNet objects, we randomly dropped them on a bunch of ShapeNet tables inside a bunch of Sun CG rooms. And then we used, PyBullet to run the physics simulation. And then we used PyBullet again to just render a bunch of images from multiple viewpoints. And this is an example of what that data looks like. So we have RGB depth and the ground truth segmentation here. Some things to note are that the RGB is poorly textured. Some of the gray objects here are gray because they actually lack any texture materials, or the object just doesn't have any textures associated with it. And also the depth is clearly very, very clean. And in our ground truth segmentation, we only care about objects that are on the table. So by doing this, we are implicitly defining our notion of unseen objects to be reasonably sized objects that are on a visible planar surface. And all of the works that I present in this talk actually will use some form or some variant of this data set. So we're going to mine what we can out of this and then see what happens in the real world. Just for comparison, this is what the real world data looks like for segmenting, or for this first half of the talk. So you can see clearly that the RGB looks vastly different. It looks real, not not simulated. The depth is also a lot noisier. There's many more holes. Sides of objects are missing due to standard depth cameras, how they work these days. So that there's clearly a domain gap between simulation and the real world. Okay, so with that set up for the first half of the talk, I'll get into the first project, which is called UOISNet. That stands for Unseen Object Instance Segmentation. So this architecture consists of a few modules. The first one, it utilizes a deep network to process a depth image into initial masks. And it produces first a foreground mask and 3D center votes. And then we combine both of those with a mean shift clustering in order to produce those initial masks. Now, processing just the depth image here actually helps us generalize from sim to real. And this is demonstrated in previous works as well, such as DexNet and this other paper published at ICRA a few years back. So that's the main reason we have this first stage only operating on depth. Now, these initial masks, if you zoom in really closely, they're quite noisy. So we next we process them with some standard image processing techniques. And then we'll take those masks, we'll concatenate them with the RGB image. We'll run them through another network, and that will spit out refined masks. And this is the final output of our network. So there's nothing fancy about this network. These blue or the green and yellow networks here, they're just units, nothing fancy about that. But the key point about this architecture is to note that we're separately processing depth and the RGB. And that actually helps us generalize quite well from sim to real. So quantitatively, we train that architecture on that data set that I showed previously. How does it perform? Well, here we've got a few metrics that I won't really explain, but the higher the better. And we have some previous works, including mask RCNN, a previous version of UOISNet, and Point Group, which is at the time, a state-of-the-art 3D center voting method. So very similar to our setup, but with at a high level, of course, differences are in the details. As any good paper will show, or hopefully to get accepted these days, you need to show some nice results. So quantitatively, we do outperform these on the real world test sets that have a clear domain gap. And that's nice. So why does it perform so well? Here's a qualitative example of why it works, or one of the pieces that makes it work. So I mentioned that last stage, there is this thing called a region refinement network, which refines the noisy initial masks once they're concatenated with the RGB. So here I have an image taken by an Intel RealSense camera at the UW Robotics Lab. Here's the RGB and the depth. You can see the depth is very noisy due to reflections on the table. The objects themselves are very squiggly. And that results in, when you process just the depth, you end up with some masks that are squiggly. They're quite noisy. The depth image just doesn't have the fidelity that you need to really get sharp and accurate masks. So these are the initial masks. And if you keep your eyes peeled on this right image here, you'll see what happens as we apply that region refinement network. And after application, we have much sharper masks. So you can see, for example, this cup handle, it's nicely segmented out. So I'll just go back and forth one more time. So this is the initial masks that are noisy. And then you concatenate that with RGB. You run it through this region refinement network and you get much sharper masks. Here's just another example from a different lab at NVIDIA. Again, some kind of squiggly masks, and we run the region refinement network, and that sharpens out a lot more. You can see the masks kind of snap to the edges of the object, which is nice. So that refinement is quite useful. So quantitatively, how much does that refinement help? Here, what I'm showing is a particular metric on one of the data sets, and this looks at the boundaries, right? And this is really what that refinement network is supposed to help. We have different versions of mask RCNN and a UOISNet without the region refinement. And when we apply the region refinement, we get some pretty strong performance increase across all these models. And the thing that's really interesting about this is that region refinement network is trained on non-photorealistic synthetic RGB. So if you remember that photo I showed a few slides ago, it's poorly textured. We trained directly on that without any kind of randomizations. There's no color jittering, no domain randomizations or anything like that. Yet it still provides a really nice generalization from that simulated data to the real world. We posit that mask refinement is an easier problem than directly predicting masks from RGB, and that's why we think it works. So once we have that segmentation, we can combine it with a grasping algorithm from ECCV a couple years ago, and we can do some fun tasks like clear a table of arbitrary objects or unseen objects. So that's kind of a fun application. Cool. So that was the first piece of work. The second piece of work here is called UCN, stands for Unseen Clustering Network. And this was published at Coral 2 years ago now. I guess 2 years is kind of a lifetime in machine learning. So maybe it's old now. So this work, it attacks the same exact problem as the previous work, UOISNet. It's trains on the same exact data set, and it has the same exact labels. So what is this network? And this is second, so it's going to be better, obviously. Why is it better? So this is the architecture for that network. Essentially, it's just a fully convolutional network. And then from that, we get pixel dense features. These pixel dense features are then trained using a metric learning loss, pretty standard, where we just take pixels of the same object and we pull them close together. And then any pixels that are further away, we push them further apart. And we train that for a very long time on this non-photorealistic RGBD data, same data set. So pretty standard. One extra piece here is that we do this two-stage zoom-in architecture. So how does that work? Well, when we take our RGBD image and we run the network, let's say we get an initial label that looks something like this. Now, from here, what we'll do is take every predicted object and we'll crop a region of interest around those. So in this case, we have 5 objects. And for each of these ROIs, we run another network of the same exact architecture. So it's the same network, but with different weights trained on these ROIs. And then basically we hope that it will split anything that was under-segmented in the first stage. So it basically takes a closer look and then does the a refinement, essentially. So that's the whole entire architecture. And so we trained this network for quite a long time on a bunch of GPUs on this RGBD synthetic data. And like any good paper, compared to previous results, we get actually quite a big boost in performance. So here in gray is the previous network I showed, UOISNet. And we're getting some quite major increase in performance in comparison. So that's nice, right? It's second in the talk, so it has to work better. So here's some qualitative results. I think the results are actually quite impressive. If we take a look, for example, at this pretty dense clutter here, we can clearly segment, for example, this small, whatever sponge thing that is, the mask itself is in the middle of this entire keyboard, but it gets the extent of both the little sponge and the keyboard itself, which is pretty nice. And then, for example, here, we can capture some really highly non-convex objects like these pliers, 2 of them, in fact. And then in this particular example here, that we've got 3 kind of small, they look like golf balls. I'm not sure what they are, but they're sitting on top of this block. And they're all segmented out quite nicely, which is a really nice result that we couldn't achieve with the previous network, UOISNet. Cool. So that's the second project. So the third project that I'll talk about for segmenting these unseen objects is called RICE. And this stands for Refining Instance Masks in Cluttered Environments. And this was published at Coral last year. And so the idea is like, how do we get even better at this segmentation task? So in this case, we changed the overall goal just a little bit. So we still have the input of a single RGBD image, but now we also feed to it an initial instance segmentation. So let's say we get this from UOISnet or UCN, any of the previous works that I just talked about. And the goal is still to output instance segmentation masks, right? We want a more accurate version. But in this case, we also want some uncertainty. And so one might ask, why do you want uncertainties? Well, to be able to perfectly segment unseen objects is an impossible task. If you've truly never seen the object before, it's natural that you'll be uncertain about the extent of the object. So we want our algorithm to also reflect uncertainties in this output. And then that can be used for downstream manipulation tasks, for example, to resolve uncertainty. So this is a high-level overview of the method, and there's going to be a lot of details that are skipped under the rug, but you can always see the paper for the details. So given the initial segmentation, we first will encode the graph, detail skipped. Now, once we've encoded it, we can sample some perturbations. So we can take some masks, we can split them, we can merge them, we can delete them, we can add them. And for each of these perturbations, we'll get a new graph or a new segmentation graph. And for each of those graphs, we can score them. And we can choose the best one that we think has the highest score that will give a refined segmentation. Or we can take all of those sampled graphs and we can compute uncertainty estimates of the object extents. And that could be useful as well. So I'll skip a lot of details, but I'll go into a small overview, a little bit of detail of some of the steps here. So for sampling these perturbations, there's 4 operations that I mentioned. For example, splitting. So let's say we have this segmentation here, and we can see at this particular point, 2 blocks are kind of segmented as undersegmented. We would like to be able to sample a split that correctly fixes that. How we do that? A bit of magic, kind of under the rug sweeping, but we might have the same thing for a merge. So if the initial segmentation over segments the serial box, we would like to sample a merge from that. Same with deleting. Let's say we have some false positive masks here, like for example, something on the table. We don't actually care about this. Let's get rid of it. And then adding, let's say we've got, if you zoom in closer, there's a piece of water bottle or something that's not segmented at all. We would like to add that back in and consider that. Details are swept under the hood, but there are deep networks underlying all of these operations. For more details, please see the paper. Okay, so that's how we sample the perturbations. Now, how do we score these newly sampled graphs, right? So after we encode the graph, which I did not describe how we do, we can simply take that graph and throw that through a standard graph neural network and output a single scalar between 0 and 1 that basically is the score in it. And when we sample a better graph, we hope that that score is going to be higher. So essentially, the goal is to train this graph network so that the better graphs have a higher score, right? That's something we'd want to do, right? So now let's say we've trained that thing. We've got our sample perturbations. We've got our graph scoring network. All right. How does this all work? How do we put it all together? So first, we start with the initial segmentation and its score given by the graph network. We can then sample a few perturbations to it, right? Let's say I sample a split, then I sample an add. Then I can sample, or then I can evaluate the scores with my graph network. I can do the same thing here and continue until I basically run out of GPU memory and basically sample a whole tree of all these graphs. And we only keep the graph if the score as given by the graph network is better than its parent. So then by design, we have a bunch of leaves that have a higher score than the initial segmentation as dictated by the trained graph network. Now, given these leaf nodes, we can compute, again, the best graph, whatever has the highest score. And we can also use all of the leaves to compute uncertainty estimates, which again, red here says, okay, we're a little uncertain about this particular object. I'm not sure if that's an object extent or not. So that's how we do it. Again, a lot of details swept under the rug there. how does this help us quantitatively? So here I've got kind of results from the previous works like UCN and UISNet. Apologize if you can hear some kind of drilling. I don't know what that sound is. Now, when we apply RICE to all of the initial segmentations coming from this, we get increases across the board on these two data sets, which is great. You know, that's nice to have. Qualitatively, what does it look like? Let's say here we've got some undersegmented stuff. When we run RICE, right, we can split them accordingly, and that looks like a more accurate segmentation. Now, what's interesting here is we look at the right side. Here we've got not just undersegmented objects, but also objects that are not in the graph itself. And when we apply RICE, we can add those back in and split the objects to get a virtually perfect segmentation, which is really cool. So that's about the using the best graph. But how do we use that uncertainty? Well, here's kind of a proof of concept of what we can use that uncertainty for, which is grasping to resolve the uncertainty. So here what I'm showing is essentially initial masks the uncertainty output by RICE. And what we do here is we select the mask with the most uncertainty, we grasp it, and then we put it in the bin. This is just a proof of concept, but you know, if we wanted to make this more involved, we can do something else with that milk carton in a separate phase, because essentially it's been singulated. So then we can, for example, build a 3D model of it or something like that. We can repeat this process until the entire scene has been understood, until there's no more uncertainty. And in this particular example, there's two interactions here, and now we're fully certain. And this would be much less interactions compared to a method that actually singulates objects, because there's 6 objects here, so that would take an order of 6 actions. So that's an example of what we can do with the uncertainty. Cool. So that concludes the first part of the talk, and I'll just briefly go over some interesting works in the second half of the talk that use the segmentation outputs to do something for a manipulation. So here we've got the first talk, and this is called ARM. This stands for Amodal 3D Reconstruction for Robotic Manipulation, published at Coral a couple years ago. So the overall goal of this work is to manipulate unseen objects by reconstructing them. And what we do is we use these reconstructed models with physics simulators for manipulation planning. So for example, let's say we observe the Stanford bunny with a single image, we reconstruct it. Then we put it with a physics simulator like Mujoko, and then we use that physics simulator with some kind of planning algorithm to plan a trajectory. We then execute that trajectory in the real world and see what happens. And of course, we want to do this in the presence of clutter because robots need to deal with clutter. As humans, we're cluttered. So what happens? So for some motivation, what happens if we take a state-of-the-art unseen object reconstruction algorithm like genre, and we apply it in this pipeline? Well, what happens is it fails because most of the time when we reconstruct these objects, they're unstable. And it gets even worse in clutter. If there's heavy occlusion, this model was just not trained to reconstruct objects in occlusion. So it just doesn't even reconstruct the bottom half of that object. So really what's going on here is that these traditional computer vision reconstruction algorithms do not optimize, or they're optimizing for visual fidelity, but they're not optimizing for physical fidelity, which is really what we want if we want to correctly manipulate these objects in the real world. So our goal is going to be to optimize the reconstruction for that physical fidelity. So what we do here is, well, here we have the architecture, or the whole method pipeline. We first have an RGBD image, and we run some instance segmentation algorithm. So, you know, this is where the previous stuff comes in, right? Now, given that instance segmentation, we run a reconstruction network. And you can think of this as exactly as like genre. It just predicts voxel probabilities. That's it. And then we throw that reconstruction into a planner with Mujoko or something, and then we execute that plan in the real world. But all the parameters that are going to be trained lie in this reconstruction network. So how do we train this reconstruction network for physical fidelity? Well, first, we need to make sure that we are optimizing a standard occupancy probability loss, which is cross entropy, right? Kind of your standard reconstruction loss. The first thing we introduced was a stability objective. And essentially what this does is says, of the reconstructed objects, the center of mass needs to be above, or the pixels underneath the center of mass need to be present. That way, the object is stable. So that's the first prior that we use, right? Because we assume a static scene. The second prior we use is that we want the object to be connected, as objects are typically not disjoint pieces. So this objective, which you can find details for in the paper, encourages that there are no disjoint parts of objects and everything is one connected piece. So how does that affect the reconstruction? Well, if we have an example like this here, where we want to reconstruct that yellow object, when we look at it from the side, if we introduce the stability objective, what we typically get is like kind of a base plane. We reconstruct that base part there. And so that makes the object stable, but it's not physically real. It's not connected, right? So once we introduce that connectivity objective, then that gives us a more realistic object. It doesn't look that great, but it's stable and connected. Minus, we did have to run a convex decomposition in order to manipulate it in the planner, but it is stable and it's connected. And so it mimics the ground truth best. Now, quantitatively, we get better reconstruction results in clutter. So if we look at genre in blue versus our method in red, and we're looking at, for example, the amount of the object you can actually see, so the percent that's visible. If you see very little, we get the highest or lowest, chamfer distance. Even when you can see most of the object, we're still getting kind of the best chamfer distance. But most importantly, in these three manipulation tasks of grasping, pushing, and rearrangement, we're getting the best task success rate. And it's a very hard problem, so these success rates are quite low compared to using the ground truth mesh. Again, here's just a quick fun video of what happens when we take our reconstructed meshes and we apply them in the real world. That's on the left. Whereas you can see the planned trajectory using genre fails. Cool. I'm running out of time, so I'll just kind of briefly go through this last paper, which is called Predicting Stable Configurations for Semantic Object Rearrangement. Again, it's another application of doing something with unseen objects. And it's always fun to see robots do stuff. So I like the videos here. So the overall goal for this project is we want to rearrange unseen object in some semantic fashion. So for example, let's say I want to place this mug in front of the blue pitcher. So maybe I want to move it like this. Or I want to place the mustard bottle behind the cookie box. And so I place it behind the cookie box, but it needs to be stable. So it needs to be on top of that other box. So how do we do this? Here's the overall method, and I'm again going to skip a lot of details. So please see the paper for more details. But essentially, let's say we have two segmented unseen objects, right? And again, this is where the previous methods come in. That's why they're useful. What we want to do essentially is sample object placements for object I that satisfy that it's physically valid. And that's given by a scene discriminator network. And then we also want that it satisfies the pairwise relationship that we specify, like behind or in front or whatever. So we need it to be physically valid, and it needs to satisfy the pairwise relationship. And these are all networks, all trained with the same, not exactly the same data set, but a variant of it. And then given that sample location, we can throw that through a motion planner to get the actual plan. Underneath the details, there's a CEM algorithm going on here, but it basically needs to satisfy this objective function. So here's just some fun results, which is place X behind Y. It could be the pitcher or mustard bottles, mugs. And in these three examples here, not only does it have to place it behind, it has to place it behind such that it's on top of that box because it's physically stable on top of that box as opposed to kind of intersecting the box. So our method can handle that in real world settings, which is always fun. Cool. So that concludes my talk. Thank you everyone for listening and attending the workshop. I'd be happy to take any questions, although I know we're over time at this point.
Thank you so much, Chris, for the amazing talk with a lot of cool videos. Yeah, I can even recognize that kitchen is from NVIDIA, and also the table and the objects. Yeah, I believe that some of the objects are still on that table right now.
Haven't been manipulated yet.
Yeah. Yeah, I see one question. So this is for the UOIS and UCN papers. So from this result, does this show that refinement, which is trained on simulation, plus robust initialization, is a good way to handle sim to real? Are there more examples?
That's a great question. For UOISnet, that is true for this particular project. It's a great point. The initialization is already quite strong, and essentially we just need to snap those those kind of squiggly masks onto the objects boundaries themselves. We haven't really tried this in too many other settings. We haven't really tested that hypothesis too much because, I mean, we had robots and we needed to get them to work, and that takes a lot of time. But that's, I think, one of the most interesting parts of that work is that piece is revealed. However, when it goes to UCN, that one actually doesn't do a refinement using RGB only, or initial mask and RGB. That thing just uses RGBD as input and predicts. And so we have hypotheses there that even though that's trained on simulated data that doesn't look great, the RGB at least, that the metric learning itself is somehow provides some kind of inductive bias that helps generalization from sim to real. That part is completely a guess, but yeah, that, just to be clear, that part does not have the same type of refinement. Yeah, but thank you. That's a good question.
Okay, thank you so much, Chris. Yeah, I think in the interest of time, we have to move on to the next speaker. It's going to be a pre-recorded talk from Jeannette Bohg, which is also be a talk on robotics and 3D vision, I believe. So let me first introduce Jeannette. Jeannette is an assistant professor of computer science at Stanford University, leading the Interactive Perception Robot Learning Lab. Before joining Stanford, she was a group leader at the Autonomous Motion Department of the MPI for Intelligent Systems. Her research focuses on perception and learning for autonomous robotic manipulation and grasping. She is specifically interested in developing methods that are goal-directed, real-time, and multimodal, such that they can provide meaningful feedback for execution learning. Oh, sounds like a perfect fit for the workshop. Okay, so let's hear from Jeannette's pre-recorded talk.
That I cannot be there in person. It just didn't work out with all the overlaps with IROS and just generally the traveling. But I really hope that you find this talk on this topic anyway interesting for this particular workshop at ECCV. Okay, so I want to talk today about object perception through interaction and look at how physical interaction, as for example done either by humans or by robots, can actually help to perceive objects better. And that is typically actually named interactive perception, which is the term that refers to the idea that physical interaction with the world actually facilitates perception of the environment. And so you see, for example, this kid here, right, is probably grabbing things and understanding the materials by actually interacting with this object, maybe uncovering occluded objects and so on. So why does this interaction really improve perception? Well, basically, when interacting with an object, you create a sensory signal that would not be there otherwise, especially if you're just looking at things. And it's particularly interesting that the signal you create depends on the action you're choosing as well. So this idea of interactive perception creates the signal in this combined space of sensory data, actions, and over time. And what is interesting is that in robotics, we have really control over these actions to deliberately create a signal in that space over time to, for example, check any kind of hypothesis we may have formed about the environment. So we wrote a survey on this idea a while back that provides this framework and a way of thinking about this idea. And we're specifically looking at the survey at robotics and putting it into relation to computer vision and active perception. Yeah, so if you're interested, you can look at this extensive survey. So let me explain a little bit more these benefits that we saw in representing a signal in this combined space of sensory data, actions, and over time with a few examples. So here's, for example, a study that was done by J.J. Gibson, the affordance guy, and that was reported on in this book on the senses considered as a perceptual system. And so subjects, human subjects, were supposed to find a reference object among these these objects of irregular shape. And it turns out that subjects were most successful if they could actually touch and rotate the objects as opposed to just looking at objects. So there's some evidence, just like one pretty old study that looks at this, how multimodality helps. There's also older experiments like this one from Held and Hein, where that studied the concurrency of motion and sending, what the influence of this is. So here the setup is that you have active versus passive kittens, basically strapped into this carousel here. So the passive kittens are on the left, labeled with a P, and they sit in a basket, and the active kittens are on the right, and they can actually walk and control kind of the movements of both themselves and these passive kittens. So what that means is that these kittens basically move through the same range of visual stimuli, which are these stripy patterns on the outside of the walls of this environment. And the question that Held and Hein ask here is visually guided behavior actually influenced by having learned how your own motion controls the visual stimuli? And so they tested this in some other visually guided tasks, like walking along a ridge or coming close to an edge and things like that. And clearly the passive kittens, or the kittens who only saw daylight basically in these contraptions, really did not fare well at these particular tasks. And so definitely compared to these active kittens. And this this kind of is evidence that the self-produced movement with concurrent visual feedback is necessary for the development of visually guided behavior. So that was another example. And then here's some fun example that was created by Octavia Camps at Northeastern, that a continuous dynamic signal has more information than just static images. And so if you look at this image, you probably don't see much. But if I do make a play, you see that there are actually dogs hidden who are playing. And this really only becomes observable over time. Any of these images, any of these frames would basically be as uninterpretable as the first one you saw. Okay, so this was just some evidence that this idea of interactive perception and looking at action and sensory data over time actually does help perception. And so now let's look at some perception problems. So here is instant segmentation as a problem, which I'm sure you're very familiar with. Basically, imagine you have a robot coming here and it has to basically grasp, I don't know, you ask it to bring 5 apples from the farmers markets. And so it really has to figure out like how these apples, how to segment these apples in order to grasp them. And so if the robot was going to do this from a static image, this is a really hard problem, as you all know. But if you look at it from a robotics viewpoint, then the robot does have the ability to actually move these objects around. And this whole problem of instance segmentation becomes much easier if the robot can interact with the crate and create some motion signal that makes segmentation much easier. So that idea of actually interacting with the environment in order to make, for example, segmentation easier is something we explored in this work. That was is a little bit older already. That was presented at IROS in 2018. But bear with me, this is gonna go to some newer work later. So basically what we did here is we assumed there's an RGBD image, so RGB and depth image as input, 2 consecutive ones. And we feed this as input to some neural network. It's like an hourglass structure, and it's supposed to output what we are mostly interested in, segmentation mask for an unknown number of rigid objects. And also scene flow, because this can be really useful more generally for a robot, but it's more like a regularizing term, or like almost like a side product. Okay, so the assumptions that we make here is that we assume all these objects are rigid, which is not a bad assumption in many application areas, if you can think so, that you can think about. But we do not know how many objects are in the scene. So the core idea is really very similar to this work that was presented at ECCV in 2019. That is maybe many of you in the vision community are familiar with, which is VoteNet. And so what they did here is to basically detect objects of different categories by using a voting-based process, where each point cloud or point in a point cloud would basically vote for the center of a bounding box, and then there would be some clustering going on, and you would get a bounding box out and then maybe a semantic label. Okay, so that work I imagine many of you are familiar with. So what we did, again, we think that actually voting in motion space is much more fruitful, especially when it and can make this instance segmentation problem actually much easier. So what we do, and published in 2018, was basically, let's say we have an object, for example, this hat here with a point, then basically we want to have each of these points in the left image here at time step t vote for the correct rigid transformation to the next image. So our voting in this particular work really happens, the voting and clustering really happens in trajectory space and not just in Euclidean space, right? So we are really voting in the space of rigid motion trajectories, and then cluster also there to do this instance segmentation. Okay, so let's break down this model that we use here. So this is basically just looking inside of this hourglass model that I showed you earlier. Basically what we do here is some magic with the encoding. Honestly, this is not so important here, but there's also some cross correlation going on. You could maybe think of this as the same encoder as what used to be in FlowNet. But anyway, what I want to discuss is actually more of the decoder, because that one is much more interesting and has more novelty. So basically there we have each pixel voting actually for the center of the object, its translation. So each pixel votes for the center of the object that it thinks it belongs to, the translation of the object, and the rotation of this object. And then from these pieces of information, we can predict instance segmentation and also scene flow. So let's look at this in more detail. So first at computing scene flow. So scene flow is the displacement of a point over time, and what of a 3D point over time, and what we know is P of I in a reference frame. But to compute scene flow, we need to know the position of this point in the previous time step at t-1. And so what we can actually do from the output of this model is to predict this point at t-1 as follows. We basically just use a rigid transformation where the center, basically the estimated center of the object, is plugged in from this output per pixel, and then we plug in the translation and also the rotation here. And this is then how we get where the point P, the 3D point at time step t is at t-1, okay, through this rigid transformation. Okay, so and given that, we can finally compute the scene flow for all the pixels in the image. Okay, that's cool, but really what we were most interested in from a robotics perspective was this instance segmentation, right? And so the main idea or the main assumption we make here is that pixels that move rigidly together basically belong to one object. And so we define a trajectory feature that looks like this, which ignores the rotation for now, just for simplicity. So each pixel now predicts a trajectory, an object trajectory in 3D space. And we are basically predicting the object segmentation by clustering in that space of object trajectories, using this voting in this particular space. And so this works as follows. Here we have basically all the points at frame t. The color essentially corresponds to their ground truth membership to a particular object. Then we use another output that I hadn't shown yet that looks at a projection of the centroid. And then also uses the radius of the enclosing sphere to really cluster objects together. So the projection of the centroid is really basically projecting the centroid into the image space, and also has some importance basically per pixel and how much it basically how important this vote is. So this is indicated by essentially the radius of the sphere. Okay, so using all of these components, we basically now cluster in the space and finally get a segmentation mask. Okay, and so how do we train this? So this is a breakdown of the loss function where we essentially have a foreground background segmentation loss. We have a loss on the object centroid that we have labeled in our data set. We have a pixel-wise loss, a variance loss, which is basically just about the clustering. That basically encourages pixels belonging to the same objects who have similar trajectories. And then we have a violation loss, which penalizes pixels that are not correctly segmented and fall outside the enclosing sphere radius. Okay, so we actually created an extremely challenging data set of graspable objects containing RGB and depth images. And these scenes here show objects falling simulated with bullet. And these are extremely challenging due to occlusions, large variety of objects from ShapeNet with different sizes and shapes. So there are 31,594 objects in there from 28 different categories. And there are really large displacements as well, which, for example, also create a lot of problems with the scene flow estimation, or a lot of challenges. This data set is ground truth labeled with scene flow and segmentation. And so just some experimental results of this. Basically what you see here is training and validation loss using basically our model that is just basically directly predicting flow without the particular structure that exploits the SA3 structure in it. And you can see that our loss that includes the structure is much lower than not including the structure. And here's some comparison with back then state-of-the-art motion-based segmentation methods. And we have like a very so we basically have a very dense method that gets less confused, but also leverages depth, and it requires only 2 frames, while this back then state-of-the-art motion-based segmentation method actually, I think, required 10 frames. So here are just some qualitative results. So on the very left, you see a frame pair, then you have scene flow, estimation, ground truth, and our method, as well as the back then state-of-the-art method. And then on the right, you actually see the output of the instance segmentation. The actual colors don't matter. What matters are the outlines of the grouped, basically, objects. And what was really exciting was to actually do directly sim-to-real transfer. So this entire method was trained on simulated data, and we basically tested it on these pairs of frames of real data. And despite really large displacement, it actually did quite well with the scene flow. For this, of course, we don't have ground truth data, and it also did really well with the instance segmentation. Okay, so this was just like one work for a specifically instance segmentation, where we exploited this idea that deliberately interacting with an object makes a perception problem that is pretty hard actually much easier. And so here is more recent work that we did on actually thinking about articulated objects instead of rigid objects, or a set of rigid objects. And so the goal here, or the motivation for this entire work, is that eventually we would like to enable robotic manipulation of a wide variety of articulated objects, so that you can just tell your robot to heat some dinner in a microwave, and no matter what kind of microwave you have in your place, it would still be able, despite this large intra and interclass variety, manipulate this object without hopefully destroying it. And so there are many recent work that made already great progress in tracking articulated objects, but often it's on a category level. And most of these approaches suffer when an object instance does not follow the assumed category-specific kinematics. So for instance, a laptop or sunglasses are pretty well-defined categories. They both always have the same kinematics, essentially. But how do you define a category for more complex objects like this piece of furniture shown in this little clip? So here initially, it seems like the object has 4 individual prismatic draws, but as soon as the person interacts with the objects, you discover it's only a revolute. And so we therefore argue, as articulated objects vary greatly in their appearance, geometry, and kinematics, to track all these objects a robot could encounter in the wild, we really need methods that do not make these fixed assumptions about an object category. And so we argue that, well, this is a good opportunity to actually leverage sample information to be more flexible during inference. Okay, so to tackle this problem, we proposed the following kind of problem structure. So as input, we only have a sequence of RGBD images without, compared to other work, any object or part segmentation available. And this pipeline also outputs a pose for each detected part, as well as the articulation model between parts. So to start, we feed each subsequent pair of images through an autoencoder, which produces a pixel-level dense motion map. And we then use this feature map to cluster pixels together that move coherently and thus are deemed to belong to the same object part. So I hope this sounds familiar, because this is pretty much what we basically did in this work before with rigid objects. But now we have actually object parts that are moving, that are each by themselves moving rigidly together. The only thing we know is, oh, these parts we assume are belonging to articulated objects. So now that we clustered them, what do we do with them to determine the kinematics of these objects? Okay, so this entire project could be considered a single time-step detector and produces individual detections for each subsequent pair of images in our input sequence. So after processing this full sequence, we aggregate the detected parts in this cluster matching step. This will give us part trajectories for each part over the entire input sequence. And so last, we construct a factor graph based on these trajectories that infers the articulation mechanism, as well as refines the trajectories to be more consistent with this inferred mechanism. And so the final articulation mechanism consists of the time invariant joint parameters and the time varying joint states. Okay, so now let me go through each component in a little bit more detail. So let's first talk about this part tracking module. So compared to recent work, our model detects and tracks arbitrary amounts of parts independent of any category assumption. So in this first sub-step, our single-step predictor takes 2 consecutive RGBD images as input and predicts the following pixel-level motion features. First of all, an importance value, which ranges from 0 to 1, and 1 represents pixels that are closest to the part center. A visualization of this is shown here. And then we also predict each pixel respective part center in the camera frame, which is again shown on the right. And last, we predict the delta pose, describing how that part moved between 2 time steps. For clarity, we omitted the visualization of this. Okay, so now based on these predictions, we cluster pixels together based on the current center, as well as the transform center at the next time step. And we can easily transform the center by applying the predicted delta pose to the current center. And within each cluster, each pixel then votes for the final part center and delta pose. Okay, so after detecting all these parts in each subsequent image pair, we will match these parts over time through the full sequence using the nearest neighbor algorithm and retrieve a raw trajectory for each part. For now, we only considered object with 1 fixed base part and 1 moving part. And in the figure on the bottom left, you can observe how we successfully extracted the base part trajectory. It's basically not moving. And on the bottom right, the moving part trajectory for the door, which is kind of like this circular. Okay, so now given these raw part trajectories consisting of part centers and delta poses over time, of the fixed base part A and the moving part B, we will use a factor graph to infer smooth part trajectories. So in our factor graph, we denote the part poses by XA on the top row and XB on the bottom row from time step 1 to capital T. And additionally, we name the time invariant joint parameters new and an additionally needed transform T. And finally, we denote the time varying joint state as Q, with which also ranges from 1 to capital T. So to bypass potential kind of mixed integer programming through making a discrete decision about the particular joint type, we will use a twist formulation in our factor graph. Similar to the recent ScrewNet work, this allows us to continuously optimize for rigid, prismatic, revolute, and helical joints without imposing any discrete choices. So for this, we will first simply multiply the time varying joint parameters QAB with the time invariant base twist new AB, and through the exponential map, we get the transformation between the base part and the moving part at a specific time step. And then we can use off-the-shelf factor graph optimization libraries to solve the optimization problem and infer the articulation mechanism. And so in this visualization, you can see the result of the linear component of the inferred mechanism for the moving part center over time. Okay, so last, we also introduce a new evaluation metric that helps us to quantify how efficiently a robot with a compliant controller would move the object based on the predicted articulation model. So to interact with an object, a robot doesn't need to know whether the object has a prismatic or a revolute joint or where each axis lies in space, but rather the robot just needs to know in which direction to push or pull roughly. And our metric exactly captures that. So given a specific point, for example, the handle of a door here, we calculate the dot product between the linear component of the ground truth articulation mechanism and of the predicted mechanism. And so here the ground truth component is orange and the predicted component blue. And for full evaluation, we integrate over the ground truth joint state range for the object. And so the resulting value ranges from 0 to 1, where 1 is the best possible value and 0 the worst. And this is the metric we will report in the following slides. So here we show qualitative examples for the factor graph compared to a different category agnostic baseline by Sturm et al. This method calculates the likelihood of all the joint types and makes a discrete decision instead of using a continuous representation for all joints, as in our factor graph estimation. And both methods use the same part trajectories as inputs tracked by our method. So on the slide, we present results when trying to track objects with the revolute joint, and the errors are the linear component of the underlying articulation mechanism. And so this is the same as the previously mentioned linear component that is used to calculate the metric. And we report the value of our metric in the bottom left of each animation. So basically, this metric is correlated with how well the error aligns with the part trajectory, or how well it actually, is a tangent of that trajectory. So the bottom left contains an example where the baseline falsely classified that joint as a prismatic, and thus the prediction error is actually quite high. The linear component does not change direction depending on the opening state of the door. And our factor graph based approach does not suffer from this problem, as it does not have to make that discrete decision of the joint type. So on this slide, you can see the same type of visualization, but for objects with a prismatic joint. As for the previous examples, our factor graph performs significantly better than the baseline, except for the example on the right. So here, the factor graph overestimated the rotation component, whereas the baseline method successfully classified the joint type as prismatic and was able to use that to bias and compensate for tracking errors. And so maybe as a last point, I want to show you also that this whole factor graph based method can also work together actually with category level tracking methods. For example, CAPTRA by Ija Wang et al. That was presented last year's ICCV. So again, here we use the output of this method, plug it into the factor graph, and then you see nicely over time how the accumulated information basically smoothes out the initial noise that is like coming from a frame by frame method. Okay, so yeah, so I hope I gave you some examples for how perception can really be improved by interaction that creates the signal in this particular space of sensory data actions over time. And the fun thing is that robots actually have control over it and can specifically create good data that helps to perceive better. So thank you very much for your attention. I'm sorry that I cannot be here in person or live to answer any questions, but I could potentially answer them asynchronously. So thank you very much.
Yeah, okay. Next, we will enter the post session. And here we already have authors in the virtual room in the Gather Town. like to host the poster session, and they will answer the questions. Next, I will share the screen about the information of the poster session. Yeah. So here is the barcode on the right side. So the attendants can scan this barcode and enter the gather talk. Enjoy the poster session. Hi everyone. Welcome back. Now we will enter the fourth session. Let me first, and that will first be the pre-recorded talk from Professor Hao Su. Let me first introduce Professor Hao Su. He is an assistant professor of computer science at the University of California, San Diego. He is the director of the Qualcomm Embodied AI Lab at UCSD, a founding member of the Data Science Institute, and a member of the Center for Visual Computing and the Contextual Robotics Institute. He works on algorithms to model, understand, and interact with the physical world. His interests span computer vision, machine learning, computer graphics, and robotics, all areas in which he has published and lectured extensively. Next, let we have the technician to help us to play the pre-recorded video. Thanks.
Hello everyone. I'm happy to share recent progress from my lab on object manipulation. The object manipulation has been a focus of my lab in the past 5 years. But today, I'm going to introduce some efforts on building a software suite that everyone can use to study manipulation, as well as our experiences on how to make it easy to conduct reinforcement learning with 3D visual inputs. As a talk in a computer vision conference, let me start from the relationship between vision and manipulation. I will use a simple object manipulation task as an example. Honeybee finds the flower and pick honey. Honeybees see the world very differently from human species. On the bottom left, the picture shows what an evening primrose would look like to us, and how it looks using UV-induced visible fluorescence photography, indicating how a bee might see it. Although bees cannot see red, so what they may see may act as black indicators instead. So honeybee's vision system fits the manipulation task of picking honey. The second example is football playing. Football players can control the flight curve of the ball after kicking it. This remarkable ability is formed from everyday practice. After many trials and errors, they know which part of the ball should be kicked and by which part of the feet, even under different airflow conditions, to achieve the desired curve. Well, such a dexterous football manipulation skill cannot be achieved by only watching demo videos. It needs practice to create the precise connection between vision and action. So hopefully, the two examples can convince you that perception, cognition, and action are intimately coupled and form a closed loop. So in cognitive science, there is the so-called embodiment hypothesis that intelligence emerges in the interaction of an agent with an environment and as a result of sensory motor activity. The key message is that interaction is indispensable in the emergence of intelligence for mankind. Perhaps this is also true for artificial intelligence. Now, the goal of my group is to study such embodied intelligence. In particular, we are interested in learning everyday object manipulation skills. Now, in fact, many groups in the vision community share the same passion as us. To conduct experiments quickly and in a reproducible manner, simulators have become a good option. And recently, there are a number of efforts from both industry and academia to push the construction of physical simulators for object manipulation. Let us review some popular setups. So this video demonstrates that robots can learn to perform mobile manipulation tasks in virtual environments. It is an internship work done by my student Jiayuan Gu at Meta AI in the Habitat 2 environment. We see the promise of achieving complex manipulation tasks in household environments. Here's another example. This is the official demo video of iThor, which illustrates the usage of the platform for high-level object manipulation plan research. Now, a third video is the official video from Yixin, the behavior, which illustrates the usage of the platform again for high-level object manipulation plan research. So these platforms are very nice in supporting the learning of long horizon and complex manipulation tasks. But if we take a closer look at it, there are certain important ingredients, or say, they adopt strong assumptions. Like in the first example, to solve the drawer opening task, there assumes a magic grab scale. When the gripper is close to the drawer, or the gripper is close to the bowl. And in the second example, to solve the egg cracking task, there assumes the egg movement is driven by some magic force and the magic crack scale. And in the third example, there is a cut scale that is magic in the sense that the hand does not really hold the knife and the onion is separated without the knife touching it. As I will explain soon, these short horizon tasks are, in fact, hard to solve. Now we call the ability to solve these short horizon tasks as manipulation scales. My understanding is that manipulation scales are the cornerstone of embodied AI. They are the basics in understanding and creating high-level manipulation plans, such as domestic service, human-robot interaction, and object rearrangement. And just like how object detection supports high-level vision tasks like image captioning, like visual question answering, like scene classification. Okay, next, let us be more concrete about why manipulation scales are hard to obtain. The first challenge comes from sensing. For example, the robot needs to grasp the handle to open the door of a cabinet. However, the door handle may be occluded and not visible by the robot in execution process, which creates challenge for interaction policy making. And second, manipulation is a dynamic process, and there might be errors in the process. A good manipulation scale needs to handle unexpected effects when accomplishing even a short horizon manipulation task. And third, some manipulation skills needs very high precision. In precision assembly, which is very important in industry, a small mistake in perception or action may fail the policy. And the fourth, there are a wide set of manipulation skills. And in fact, for our daily life, we humans use a combination of all of them without any trouble or even thinking. Now, for example, using a plastic bag, which is a deformable object, is a very big challenge for the moment in manipulation skill study. And lastly, as in object recognition, the variation of object topology and geometry creates a big trouble for manipulation skills. And getting such kind of generalizable scales across objects is hard. So I believe that the difficulty of manipulation skills necessitates the collaborative research across groups in the world and fair benchmarking of the progress. I have been thinking about the problem for quite a while, and now in computer vision, we do have a lot of past successful experiences on this. Like ImageNet pushes 2D vision and ShapeNet pushes the 3D vision. So they are public resources to the entire community. In the case of manipulation skill learning, perhaps we also need such a thing. I'd advocate to build simulation environments which rich 3D assets and tasks. And the ideal simulator needs to achieve the following goals. Now, it should make it easy for any group in the world to reproduce experiments by others. It should make experiment cost low so that more groups and individuals can join the force. And it should allow researchers to access rich interaction information, and that helps to debug the algorithm, the system, and to push hardware design. And it should be realistic enough to verify the usefulness of algorithms for manipulation skills. Realistic. And it should support fast research and development cycle so that solid conclusions can be reached and propagated. Now, with these concerns in mind, my group pushes the Sapien simulation engine and the many-scale manipulation skill task set. Next, let me share some latest progress. Now, here is the outline of today's talk. I will use 10 minutes to introduce the Many-Skill 2 challenge for benchmarking manipulation skills. And then I will introduce an important algorithmic trick on how to achieve efficient 3D reinforcement learning. Let me start from Many-Skill 2. To push the benchmarking and learning of manipulation skills, my group spent several years to build a physical simulation-based task suite of object manipulation skills, which is called the Many-Skill Challenge. This summer, we have released the second edition of the Many-Skill Challenge. The Many-Skill 2 includes 20 manipulation task families with 2,000 plus object models and 4 million plus demonstration frames, which cover a stationary, mobile base, a single or dual arm, and rigid or soft body manipulation tasks with 2D or 3D input data simulated by fully dynamic engines. It defines a unified interface and evaluation protocol to support a wide range of algorithms, like the classic sense plan act, reinforcement learning or imitation learning, the visual observations like point cloud or RGBD, and controllers like the action type and parameterization. Moreover, it empowers fast visual input learning algorithms so that a vision-based policy can collect samples at around 2,000 frames per second with 1 GPU and 16 processes on a regular workstation. Let me review its key features one by one. The first, it features providing a rich space of tasks. Below picks 4 representative tasks out of the 20 task families we provide. In terms of the physical property of the objects under manipulation, we support benchmarking rigid body, articulated body, soft body, and fluid. In terms of robot morphology, we support single arm and dual arm robots, and we support parallel gripper and specialized end effector. Now, in terms of mobility of the robot, we support robots with a mobile base and those with a fixed base to the desktop. Our second feature is on an important but often missing function. Now, in embodied AI research, it is a big challenge in how the action signal should be represented. For example, your algorithm can output a desired position or velocity as the control signal, and representation of the position and the velocity must be in an appropriate corner space. And for the research over the synchronization of vision and hand, choosing the best action signal is extremely important. And the choice of action signal and its representation would make a difference in the sample complexity and the generalizability over the learner policy. Remember that each action signal will correspond to a type of controller. And for example, for object picking, it's simpler if the action signal represents the location of the ND effector, which corresponds to the so-called task space controller. Now, whereas for collision avoidance in motion planning, it requires action signal to be all joints of the arm, which corresponds to the so-called joint space controller. To allow users to freely choose the action signal and its representation, we provide many controllers and we provide auxiliary functions to convert action space of demos across controllers. To accelerate the research cycle for visual policy learning, we also present a highly efficient system. We're going to release a major update on ManyScale 2 around the end of this month. For this new system, on a single GPU, the system can achieve sample collection speed of over 2,000 frames per second. Now, the system also has a low memory footprint, thus make many environments can run in parallel. This will greatly accelerate the training of RL. The key to the speed of the latest ManyScale is because of its highly efficient rendering pipeline. It uses asynchronous rendering so that all parallel environments share the same rendering process. And this design could largely increase the utility of CPUs and GPUs. Next, let me use some example tasks to give you a better sense. So this is the example of soft body visual imitation learning. The task is to pour the water into the beaker until the water level reaches the pre-specified red line. We tried the naive point cloud-based behavior cloning method, but the policy cannot really achieve the task. On the other hand, if we provide the detective composition to the robot as an input, the behavior cloning could work. That illustrates the importance of what to perceive for interaction. The second example is a faucet turning task. The faucet is an interesting object, that the way to turn it is different based on installation. But humans could roughly infer the way to use it by just seeing it. Now, there are many challenges that make this task hard. For example, not only to predict how to use the handle, for some poses, avoiding the collision of the arm with other parts of the faucet when it's moving is just hard. And finally, there are two tasks inherited from last year to push a swivel chair with small castle wheels installed on the legs, and to move a bucket with a big ball in it. They are the so-called under-actuated systems because the dimension of the degree of freedom is higher than the dimension of the control signal. And for this task, there has to be collaboration between the arms to make the movement successful. Okay, so because the system is under-actuated, it is hard to be solved by traditional analytical algorithms. To build a good simulator for robot learning, a lot needs to be done. And we hope that our work can save the time for users of the environment. Let me show some example efforts to improve the ManyScale and the Sapien system. Now here shows the full technical stack of ManyScale. At the bottom level are the low-level resources, which are the public libraries widely used in the community. On top of it, we build renderers and simulation engines. The renderer supports both rasterization and ray tracing, and the simulation engine supports both rigid body and soft body. They are customized with speed and quality trade-off for embodied AI tasks. We also convert ShapeNet models to be simulatable by introducing the PartNet mobility dataset. Then, on top of the renderers and simulators with efficiency and speed balance, we build the task space, which is the many-scale tool you just saw. On top of it, we also provide many useful tools for planning, control, and learning. In particular, we did some work to pre-process geometries to make them fast to simulate without changing its behavior for collision. For rigid body or articulated body, our 3D assets are represented as URDF files, which includes meshes. For the simulation of meshes, it is slow to compute a collision between general meshes. However, if the mesh is convex, the collision computation is a lot easier. We, therefore, study what is the best way to decompose meshes into convex bodies. Our SIGGRAPH 2022 paper proposes an algorithm named COCAD, which is a collision-aware, approximate convex decomposition algorithm with theoretical guarantee. Now look at the picture on the right. With our method, the decomposed shape preserves the hole for grasping, whereas the baseline method fills the goal and affects the graspability. We are using our algorithm to process all assets for many-scale too. Besides, Sapien also provides a physics-grounded depth sensor simulator. In Sapien, we simulate how a stereo sensor builds the depth image so that the sim-to-real domain gap becomes very small. After optimization, the system can capture the depth map of virtual scenes at over 200 frames per second. Though this function is not integrated into many-scale for speed considerations, it can already be found in the latest Sapien release. So previously, I introduced how we built the many-scale tool benchmark for manipulation scales. And next, let me introduce an algorithmic effort for how to learn the 3D reinforcement learning. Let us think of how to build the neural networks to learn manipulations. In a community of manipulation learning, especially reinforcement learning, the majority of works assumes 2D images input. But interaction takes place in 3D space, and therefore, 3D input representation should allow easier relationship reasoning. Now, think of an example. In the grasp pose prediction literature, back to 2016, the mainstream method uses 2D CNNs to predict grasp poses. Now, most works on grasp pose prediction will take 3D point cloud as input and make predictions in 3D space natively. The story of grasp pose prediction to move from 2D to 3D naturally asks a question: should we also extend visual RL from 2D input to 3D input? With this question in mind, my lab strives to seek for its answer. Then we use many-scale as the environment to do experiments. Many-scale provides 3D sensory data as the input. In many-scale 1, we provide a point cloud captured by a panoramic depth camera. And in many-scale 2, we also add the hand camera. Here's the first-person visualization of the point cloud. So we made many attempts to improve the learning efficiency of reinforcement learning when we used PointNet to build the policy and the value networks. In the end, we find an important trick and would like to report here. So for policy learning with 3D point cloud input, we have to think of a very basic question. Now, each point in a point cloud is an XYZ coordinate. And which coordinate frame shall we choose to represent this coordinate? As an example, think of training a PointNet-based policy network to push this chair. The candidate coordinate frame to represent the point cloud includes like the world frame, and the effector frame, like the left and right and the effectors, the robot base frame. Now, if the object part, like chair arms, are detected, we can also have the targeted part frame. In supervised learning, such as object segmentation, the vision people already know the importance of choosing coordinate frame. There are certain effects. We find that in 3D RL, choosing the right frame is actually crucial. Now, in some frames, 3D RL just cannot learn anything, while in some others, they could learn very fast. Let me use an example to convince you. First of all, different coordinate frames canonicalize inputs in different manners, which is essentially performing various alignments among the point clouds across multiple time steps. For example, in the ND effector frame, the ND effector is always aligned at the frame origin throughout a trajectory. Such alignments may simplify the learning of visual modules in distinct ways. With the ND effector frame, the network does not need to locate an ND effector in point clouds, which is always at the origin. Now, similarly, with the targeted part frame, it can be easier to determine the relative position between the targeted part and the robot ND effector. So the robot base frame naturally aligns its frame axis with the moving direction of the robot's base. And therefore, choosing the proper frame can convert the binary relationship inference problem to a unary object localization task. Now, we empirically compare the 4 coordinate frames on 5 distinct physical manipulation tasks adapted from many-scale and OCR TOC, covering various numbers of robot arms, robot mobilities, and camera settings. The results show that the choice of frames has profound effects. In particular, the ND effector frame and the targeted part frames, which are rarely considered in previous works, lead to significantly better sample efficiency and final convergence and the widely used world frame and the robot base frame on many tasks. This observation is consistent across 3D backbone networks. However, a single frame can perform well on some tasks, but poorly on others, and we wish to find good frames in a task-agnostic manner. Moreover, for complex manipulation tasks, a single frame can be insufficient. For example, when robots are equipped with multiple arms, each arm may have its preferred coordinate frame. In addition, many tasks involve simultaneous navigation and manipulation. The figure here shows 3 stages of a move bucket trajectory. The first, approaching the bucket. The second, moving the bucket to the platform. And third, placing the bucket on the platform. In such cases, different frames could benefit different scales, like the robot base frame for navigation scales and the effector frame for manipulation scales. And therefore, it is of great help to propose a task-agnostic method that can automatically select the best frame for multiple candidates or combine their merits. Now, in this work, we present a collection of strategies to adaptively select and fuse multiple candidate coordinate frames, and we call them frame miners. The figure here shows the pipeline of frame miner mixed action, which is inspired by the idea of mixture of experts. Specifically, this approach takes a fused point cloud and n candidate coordinate frames as input, and first transform the point cloud into n coordinate frames. For each transformed point cloud, the FMMA architecture employs an expert network consisting of 3D visual backbone and an MLP to propose full robot actions. There are M joints in total. Now, since different experts use different coordinate frames, they are encouraged to specialize in different scales and controls of different joints. And finally, we combine actions from the N experts through input-dependent weights. And every frame could adaptively change its weight. So we predict the weight for each pair of expert and joint. And for each joint, we normalize the weights over the N experts via softmax and fuse the actions through a weighted linear combination. Okay, so we have multiple discoveries throughout the experiments. We find that on single frame, a single arm task, our frame miner performs on par with ND factor frame, which suggests that the frame miner can automatically select the best single frame. And on those dual RM tasks, our frame miners can significantly outperform single frame tasks. And that's demonstrating the advantage of coordination between multiple coordinate frames. While it matters to fuse information from multiple frames, the specific frame miner to choose does not create much performance difference. And we also find that for mobile manipulation tasks, base frame dominates when the robot is in the navigation phase, and the effector frame will dominate in the manipulation phase. At the end, let us draw the conclusions from today's presentation. We see the importance of manipulation skills, and also we introduce the efforts in building a benchmark for manipulation skills and building a stable 3D reinforcement learning framework. In the end, I'd like to acknowledge the great efforts from my students at UCSD and also from my collaborator from Tsinghua University. And I would also like to thank the support from NSF and Qualcomm to make this happen. Okay, thank you very much. And I'd like to take questions.
Okay. For how to give this pre-recorded talk. And next we will move to Professor Yixin Zhu. Can the technician like disable the record? Yeah, I mean, during the time, I can first give an introduction to Professor Yixin Zhu. He is an assistant professor at Peking University and executive research director of Big AI. He received his PhD degree from UCLA, advised by Professor Sungjin Zhu. His research builds interactive AI by integrating high-level common sense, like functionality, affordance, physics, intent, with raw sensory inputs, for example, like pixels and haptic signals, to enable richer representation and cognitive reasoning on objects, scenes, shapes, numbers, and agents. He directs the PKU Cognitive Reasoning Lab, working on abstract reasoning, visually grounded reasoning, and interactive reasoning. So next, let's give the time to Yixin Zhu. Yeah, Professor Yixin Zhu, you can share the screen. Yeah.
Okay, let me see if I can share the correct one. Okay, can you see my screen?
Yes, yeah, we can see that.
Okay, perfect. It's working. Hello, everyone. Thanks, Jiayuan, for the nice introduction. I'm the last one, so I'm gonna act quickly so that we can have panel discussion on time. Today, my talk will be on the theme, on two themes actually, from human-machine interaction to human-machine teaming. So before diving into these two things, I want to talk a little bit more at a high level. So a popular view today is what we call ABCD view. So AI equals to big data plus computing power plus deep learning. So this is perhaps a very common view of today's AI, and perhaps not completely wrong, right? Everyone is using a lot of data, a lot of computing power with deep learning to train their model for certain tasks. But I hope by the end of my talk today, I will convince you this view only sees the tip of the iceberg. So you see only what's on top of the sea level, but what underlies the sea level is the majority of the vision. So over the years, we have seen we are shifting computer vision tasks from the left to right. For example, from the simple recognition, we can almost claim that we solved the recognition, right? In certain recognition data set or benchmark, AI already beats human performance. But on the right, these are the tough tasks that right now AI is still far, far away from human performance. For example, recognize or understanding causality, predict the intent or goal of agents for complex tasks. People seem to be stuck with more complex tasks. But in my view, or in a few people's view, the reason is if we can't solve a simple problem because we have to solve a more complex one. So in order to solve, for example, recognition problem, the left 5% or left 3%, we have to solve a more complex task. Let me show you an example. For example, this is perhaps one of the simplest tasks if we have a robot at our home, right? So if you have a home service robot, it makes you a breakfast, the simplest one, milk and cereal. Okay, this is very simple, right? You just need to grab a bowl, grab the cereal, put the milk in, and get a spoon, right? Simple. But even if we can solve the recognition task at ease nowadays, this is likely how we can get the robot to do, right? This is why Professor Hao Su presented his last work in the last talk, right? So you can see it's not a problem of recognizing the object. It's really a problem that the robot or AI in general have trouble understanding what the task actually entails. For example, what the making breakfast entails a person or AI to do. Okay, let me show you another example. People may say, okay, we just need to mimic in the human demonstration, but it's not the case, right? So if you mimic human using a hammer to crack a nut, this is likely what the current robot can do, right? It will fail because there are different embodiments of the robots. The right way, if you want to make this robot work, is you have to have a novel to use strategy that is very different from human to use. Okay, that's all my motivation. So today I'm gonna start with a question, how to define an object or a thing in general. Second, I'm gonna dive into the two things in the title. First is how to interact with object. Another one is interact with agent, that is teaming. For the first one, I want to talk about task-oriented representation, functionality, and affordance. The task-oriented representation is the core of the entire talk. And given this representation, we'll see how we can understand what is happening. And then I will talk to new work that is currently under review or just got accepted in Europe. One is articulated object, another one is language conditioned motion generation. In the last part, I will touch briefly on the theory of mind and value alignment. Okay, the first part, how to define an object. I say it is a task-oriented representation. Okay, this seems to be very strange to a lot of people. What is task-oriented representation? Most people understand computer vision from Mars' book, right? Mars said, okay, computer vision is to compute what are where by looking. This largely dominates computer vision in the past 50 years or even longer, right? This actually also corresponds to human brain. There are two major pathways. One is called dorsal pathway, another one is ventral pathway. The dorsal pathway roughly corresponds to the where, meaning that it's in charge of reconstructing depths, shapes, scene layout, etc. And the impairment of this particular region will lead to the disability of certain reconstruction, depth, shape, perception, etc. And the ventral pathway is almost similar to what we call the what area. Basically, it's categorized object in things. And this largely leads the past, particularly the past 20 years computer vision project research. We achieve very good results on video surveillance, image search, and perhaps some other applications. But frankly, if we ask what is vision for and how far are we to build a biological-like vision system, this is still very, very far away. Okay, but what is vision for? Let me show you one example. This is a study done almost 20 years, well, more than 20 years ago by a psychologist. So the task is, if you put an agent into a completely new environment, for example, a kitchen here, what would he do or she do, right? In the end, if you ask the agent to make a coffee, they can just skim through the environment, like the embodied AI research we currently do, but beyond navigation for sure. Okay, it involves complex manipulation and task understanding, but strictly during executing this subtask, human only take a glimpse of time to do it. And this is using a single biological visual system, not 10, not 20, a single one, right? So what is vision for? My answer is the vision system is to handle a wide range of tasks. Okay, in summary, if we take a further step back, we can view computer vision as three phases. The first phase really starts as a geometry based or geometry centered. This largely dominates the early vision, right? And the second part is the view centric or appearance based. This is we are very familiar with it, right? The image recognition task, categorization task, all fall into this category. But another one is what we call task-centric or task-oriented. This is also a theme that we host several times. The workshop we host several times in the past few years. Well, not recent 2 years, but a few years ago. And we call this the dark matter and the dark energy of computer vision or AI. And the task-oriented representation is not really a new thing. It's already studied 30 years ago. From my understanding, well, the earliest one I can find is the one done by Yixin and Marshall Haber in 1992. So in this particular IROS paper, they did a study on recognizing object, how to grasp it by analyzing, okay, a single object, how many times, how many different types of grasping you can afford. For example, if you want to grasp a mug, you can grasp the side of the mug, or you can grasp at the bottle, or you can grasp at the handle, right? There are multiple ways to grasp it depending on the task you want to accomplish. And this specific perspective has been echoed by psychological studies. For example, this one, if you ask the subject to recognize, okay, this is a restaurant, this is a region where they will look to or pay attention to, right? If you ask them to say, okay, this is a cafeteria, they will look for completely different regions. So this indicates that human vision organized representations, and thus the inference process for categorization, categorical recognition task. My interpretation of this robotics or psychological studies are people represent various activities, or we say tasks, for different thing categorization tasks. And imagine typical task and search for their associated object for quick verification. Like the one shown here, given the scene, we imagine people standing in front of the object or sitting next to it, or even lie on top of it. And recently, our group has done a few work on these topics. For example, this particular scene parsing project, basically we say, okay, the scene parsing is not really just to reconstruct the 3D scene, but also you have to accomplish a few tasks in order to make sure the reconstruction is good. Okay. Next, I want to talk a little bit of understanding object in the context of a task. So object is arguably more complicated than scene because it requires a finer level of understanding. For example, if we want to crack a nut, like the video show here, this is not a trivial task to understand, right? So in the wild, chimpanzees understand this task by looking at their adults. And it still takes years, some say 7 years, some say even 10 years to accomplish or master this particular task. In this particular example, you can see the baby chimpanzee didn't get the concept right. So it still struggles to open the nut. And this cracking a nut example also have some analogical tasks. For example, opening a beer, right? People will say, okay, if I don't have a beer opener, how can I do it? In fact, if you search on YouTube, there are thousands of ways to do it. And each object can be served as a beer opener, right? So in this particular one, the object understanding task is way beyond recognition, right? You can't use categorical label to say, okay, this particular object is a mug, but in fact, it's a beer opener, right? So in fact, the understanding is simply much complicated than what we would think. in summary, object used as an opener in the task of open beer is just more general than object recognition. And this particular view is not only limited to the object, but also can be generalized into the scene, right, shown here. And let me talk a little bit on how we do it from object recognition to object understanding. So first, we learn from one example, right? So here, literally one example. You see a person pick up an object and crack a nut. And in the testing case, you want to generalize and innovate on completely different scenario. That is, given a task and a set of objects, you want to imagine which tool to use and how to use it. And therefore, you have to calculate the physics, how to change the object fluence. And this particular view is what we call, again, task-oriented representation that require joint spatial, temporal, and causal reasoning of the entire process. Well, I think I have to pick up a little bit faster because the time. Okay, so here summarize the computing process. Due to time limit, I will only show this one slide. So imagine you are watching a human demonstration like I showed above. If you assume this person is rational, that means this person is really trying to teach you instead of hinder or play something funny. That means he is trying to optimize something. So if you happen to pick the right concept, the passing of these events will likely lead to an almost optimal strategy of this performance. For example, it's optimizing the force. Otherwise, if you pick the wrong physical concept, the observed one is unlikely to be the optimal one, meaning that if you randomly sample another strategy, it may outperform what you see. Okay, these are some examples after we use this algorithm. So you can see we can learn from normal tools, household object, or even stone. Okay, summary of the first section. I want to show you how we are going from kind of big data small task to the small data big task setting, meaning that you are not only driven by the data, but also driven, or more importantly, by the tasks. This is our dream of to show, okay, maybe perhaps the robot can achieve a certain level of autonomy, like the video shown here. This is from a game, but very similar to Professor Hao Su's work demonstrating in the embodied AI or manipulation tasks that we want to achieve. In the end, we want to say, ask a question, what would be a good benchmark for the task? Sungjin's daughter has a very nice painting, How to Reach the Moon. So if you are interested, you can go to his website and read the blog. Basically, there are different strategies. One is if you look at the well, you can see the shadow or reflection of the moon, right? So that is one way you seem to be closer to the moon. Another way is you climb the tree, you become higher and higher. You seem to be closer to the moon. Another one is you actually build the rocket. So everyone knows what would be the correct way, but in order to solve a complex task, you sometimes just need to build the rocket instead of climbing the tree. Okay, that's the first part. The second part and the third part will be very quick because it will be largely an overview of the recent work. So let's start with the interaction. Looking at these two videos, can you tell what's the difference between these two bottles? Let me pause a little bit. Okay. The answer is one of the bottle is child safety bottle, meaning that you can't open it by simply twist it. You have to push and twist, right? So this level of understanding the causal mechanism underlying object interaction is crucial for a lot of object manipulation or interaction. And to tackle this problem, we actually start with building hardwares. Funny thing, I spent quite a few years on this particular project. And in the end, we have a tactile sensor layered on top of a glove. And this is a particular iteration of the hardware evolution during a few years. You can see the size gradually shrink to a very small one. This is a quarter. And this is what we have. So you can see, open this bottle. If you simply twist it, it won't open. You have to push and twist. To really unlock it. So this kind of understanding is really subtle, and you can't really infer from the visual alone. And using this graph, we actually achieve very high fidelity graphs in VR for training purpose. And the next step will be, okay, if you understand this particular process, can you teach the robot to do it? We say we can. And this particular work published 3 years ago on Science Robotics is indeed leveraging these haptic signals combined with visual signal. And the robot actually needs to not only understand the haptics push signal, but also understand the action sequence, when to push, how many times it push in order to open the bottle. Okay, 2 new work. One is we recently moved towards articulated human-object interaction. So human-object interaction coming into a whole new level. And this work is still currently under developed or under review, depending on what you say. So in this particular data set, we call chairs. It captures human articulated object interactions. So here, the next video shows the exact setting. We use a motion capture system with a few cameras. On top of a human body, we put a lot of sensors, trackers. And when the person moves, basically we can reconstruct 3D in very high fidelity. Okay, these are some results. So each video on the top right is the reconstructed one. And here are more. You can see the variety of the interaction with the chairs. And here more. And this is all the objects we use for interaction. And you can see the articulation are with a lot of variety. Okay, since it's under review, I won't go into the detail. We are likely to release this data set with a paper on archive early next month-ish. The next work is the language condition. So from the articulated object, we also work on the language conditioned human-scene interaction. In this particular work, we hope to generate the motion sequence or synthesize the motion in a semantically consistent way with an input language. So in short, we basically fuse 2 existing data sets to generate a completely new synthetic ones. Here are some examples, from walk to sit to stand up to lie down. The model is quite straightforward. Basically, you can think of it's a multi-model input method that you have not only a point transformer that handles all the point clouds, but also the bird that handles the language input. And here are some qualitative results. Okay, last 2 minutes, I will quickly go through the last part, interacting with agents, that is human-robot teaming. So this particular work recently was featured on Science and Science Robotics front page, recently accepted to Science Robotics. We study the problem of value alignment. So artificial intelligence and human-robot interaction are subject with rich origins. Back in 1940s, American science fiction writer Isaac Asimov created 3 laws of robots and pictured future human-robot interaction in his science fiction short story, I, Robot. And inspired by this work, novel, our work actually tackles very difficult or challenging user-machine collaboration task. In particular, we set the game as a bidirectional value alignment. So in this particular game, the human user understands what are the critical values, but the robot doesn't. And the robot has to work as a team to explore all the area. Some tasks are require the robot to move fast towards the goal. Some require to get as much resource as possible. So follow the convention, the value function defined as a combination of a few factors. Right? So it's a simple linear combination of all the factors. And the robot has to infer this all the weights, all the factors from during the interaction with human. So this is an overview of the entire work. So given the current state, right, or we call the observation, the robot and the human has to both infer each other's mental model and then generate a planner. So the robot will act based on this planner and generate the explanation. The user will approve or reject the explanation, therefore update each other's mental model. And this is a more formal way. Due to time, I don't think I will explain in detail, but let's see a video here. So this is actually how the system works. Playing? Yes, it's playing. It's working. Oh no, it used to work. Anyway, moving to the last one, we designed a human study with 3 different groups. And in the end, we see that the human user actually align quite well with the robot, very fast. Actually, at the 25%, the human robot are almost reaching the same level of understanding. And also, humans are better able to estimate score the value function as the game progress. I think that's all my talk. It's a little bit rushed, but I want to fit as many content as possible. Thank you all.
Yeah, thanks, Professor Yixin Zhu, for the interesting talk. In fact, you have like maybe at least 3 minutes left for you. I mean,
Okay.
the 60:45 is the expected time. Yeah, we will glad like if you want like to maybe we can discuss some details about your work.
Mm-hmm.
Yeah, I think that maybe I can first ask some questions about your like work. Currently, I think maybe for the robotics, many research just to use the grasp pose as like a proxy representation or like intermediate representation to connect like the planning and like perception. So for the perception model, they just need to predict the grasp pose, and then they use like IK, the inverse kinematic, to compute the joint positions, and then they use this thing, like they can do some long horizon things, but they just predict the sequence of grasp pose. So what's your like opinion about that? Like, do you think it's suitable, like maybe for the final embodied AI things, like whether we can still use the grasp pose, or we need to like find other ways that, or other intermediate representation, or we can use some end-to-end way to get representations. So like we would like to hear from your like ideas. Yeah.
That's really a good question, but I have to break it into several aspects. So the first is planning important to accomplish this kind of task or this type of task? The answer, in my opinion, is yes, we need a planner. Otherwise, we can't get the robot working everything on RL or deep learning, right? It has to form a certain level of abstraction. Therefore, you can plan for different tasks. In fact, our group recently have a few papers tackling the planning problem. The most important issue, in my opinion, is previous planning problem treat each body parts of you, or the tool, or the thing as individuals. So therefore, it's very inefficient. We recently proposed a very efficient way to represent the thing as a kinematics chain. Therefore, it's improved efficiency. So that's the first part. The second part is whether the grasp representation is sufficient. I would say certainly not. Although we definitely need grasp and we definitely need planning, but I wouldn't say the grasp is a particular efficient representation for the thing or this kind of task. I don't have the answer to say, okay, what is the proper representation? But in my opinion, it has to leverage the same context, not only the grasp alone. People will say, okay, if I have object-oriented representation that include every context from this object view. In theory, yes, if you see enough data, enough different type of things or interaction, you could encode everything into it. But in reality, I would say it's very difficult. So you have to have a way to encode whatever the same context into the interaction. So that's the second part. I'm not sure I have a third part. If I do, I must forgot. But I think that's all for now.
Yeah, yeah, thanks for this answer. Yeah. Yeah, like we like in our group, for example, like Professor Haosu's group, we also like working on like similar things. Like we try to find the representation, like grasp pose, for example, we have some task that like we need to turn on the like the forset. But like for the traditional like planning things, like because for example, if we want to like TAMP, the task and the motion planning, we usually assume that like when the gripper or the end effector contacts the target objects, then we think like they are connected, like we lose like 1 degree of freedom, so then we can plan it. But for like some tasks that require much like some contact rich tasks, this kind of thing maybe not hold. For example, if you want to like hold some objects, but you push to the wall and against the wall, then you want to rotate the things, then the totally their things cannot be easily planned with like traditional, like, I mean, with like naive motion planning, right? So it's something that like, I mean, grasp pose itself is not enough. Like you cannot directly predict the end effector pose. It's not like a static process. It's like a totally dynamic process. So do you think, like, do you have any idea, like maybe what's the like representation that somehow can help like to solve this kind of dynamic problem?
Indeed. So I think it is actually connect to what they call active vision, right? So you think you know how to manipulate this particular object based on your experience. You go there, you try it, it doesn't work. Therefore, you have to adjust your strategy, not in the RL way, but in a way that summarizes all your previous error and generate a completely new one that you never tried before. Given this particular context, this definitely requires some novel thinking that I don't have the clear answer to you, but I think this is the right way to go. That you have to, going back to the 2 points I said, you have to have a planner. This has to have, no matter whether it's differentiable or not, but you have to have in order to generalize. The second one is you have to have enough expressiveness of the representation that not only encode whatever the task is, but also encode the same context.
Yeah, I think like many I mean, the panelists are here now. Maybe I can leave the time to Shubham and Yanchao. Okay, yeah.
Hello.
Yeah, thanks. Hey, hi Yixin. Hi Yanchao. Hey, hi Thomas. Hi Chris for joining. Thanks for joining.
Hey.
Hey.
Thanks for the invitation. Nice to be here.
Yeah. So maybe we'll wait a couple more minutes because I think 2 of the panelists might join us, and then maybe we can get started. Okay, so yeah, I think we're waiting for Niloy and Klaus, and we'll just give them a couple of minutes. Are any of you actually at ECCV and attending this workshop sort of remotely from a hotel, or are all of you also purely remote right now? Okay.
Fully remote for me.
Okay.
Same here.
It's very hard for me to travel in China. It's extremely difficult.
Okay, so we almost have everyone. Let's just give Klaus a couple more minutes and then we can get started.
I think
Yeah, Klaus just mentioned he's on his way, so he should be here in a moment.
Okay, perfect. No, are you there in person, Eloy?
no, I'm
No,
in.
okay.
Maybe I missed something. The time zone looks a little bit off from the schedule. Did anything change? That's why I was a bit surprised.
So I think based on the initial plan, maybe like a week back, we had one talk that got cancelled due to some reasons, and so things
I had
moved up by a bit.
maybe I didn't refresh this. I have an old. Yeah, that's the case. Yes, indeed. Yeah. Okay. I think one advantage of not being in person is to being able to attend some of the other talks. There's quite some good workshops going on today.
Yeah. Makes it slightly easier to move around virtually compared to in person, where you have to run between different rooms and figure out amongst sort of the 50 rooms, which is the right one. Okay, maybe we can get started and hope that Klaus just joins us in a couple of minutes. Yeah, thank you again for taking the time to come for the panel, and thanks for your talks earlier. So today, I think to get us started, Yanchao and I had prepared some list of questions, basically hard questions that we don't know answers to, and we thought we'll sort of cheat and ask you guys for all the right answers. And if there's sort of someone in the audience who wants to ask questions, feel free to do so in the ECCV portal. We'll be monitoring that, and after we are through some of the questions that we had in our mind, we can move over to some of the audience questions as well, if there are any. And yeah, I think I'll maybe pass the ball to Yanchao to get it. Oh, I think Klaus is here as well.
Yeah. Thanks everyone for coming. So our first question is, so everyone can answer, but we have this designated Christopher and Klaus for this question. So the question is, what are the major principles and challenges to unsupervised object discovery? And would multimodality be the key to resolving the difficulties there?
Klaus, feel free to take this one, or you can start.
I can try. Thanks for the question. That is an excellent question. I'm not entirely sure I know the answer. I think the main challenge to me personally is to know how to evaluate. I feel objects are one of those things that are so intuitive. They obviously make sense. They are clearly at the center of a lot of our reasoning, of our thinking, of many things. And yet it is frustratingly difficult to find out what exactly is the thing, like in terms of numbers, in terms of metrics, that they should afford. I think interactivity is actually probably the answer in that regard. I think interacting with the real world and trying to, like robotics, trying to accomplish some task is probably one of those domains that is really almost impossible to get done properly without proper object representations. But it's also difficult to find a task that we can agree on as being representative as a metric.
Yeah, I completely agree with you on all those accounts. I wanted to add just a couple of things there, kind of breaking down pieces of the question. So I think really the definition of an object, is kind of key here. And at the moment, we don't have technologies that are able to handle what all possible types of objects or what a human would consider an object. So really, it's kind of a task-dependent definition. And that I think really helps to kind of, focus that challenge a little bit. And then also the word unsupervised here, doing this, we've had a lot of great talks in this workshop, and really how people attack this in a unsupervised fashion is quite different. For example, Sungjin is using these kinds of like slot attention mechanisms, right, which is purely unsupervised. Whereas, a lot of roboticists, if you define unsupervised to be no human annotations, we like to generate simulated data and try and use that. And that tends to work quite well for certain settings, right? So that's also something I wanted to point out. And really, I ultimately agree with Klaus that I think interaction really is going to be what is currently the dimension I think that needs probably the most work, or is the most underexplored, I would say. In those settings, really, is when we'll be able to fully, or hopefully, when there's a lot of research in that direction, when we'll really be able to understand objects and discover them, not just their shapes, but their textures and their what kind of haptic feedback you get from it, that kind of stuff. So it'll be exciting to see more and more work in that direction, and I think that will really help overcome some of these challenges for discovering objects.
Thanks for the nice answers.
Yeah, thanks. So actually, yeah, that touched on a lot of interesting points, sort of on interaction being important, on the definition of objects not being very clear, which we want to revisit as we get into the more philosophical part of the discussion a bit later. I also had, even if we, let's say, agree on what notions of objects are, or nice rigid objects that we often start with, even in context of those, one thing that I sometimes get surprised by looking at sort of the overview of the research is sort of all representations we tackle, or sort of even if there's a volumetric representation or there's an implicit neural representation like nerve, they're all representing objects in a metric space. Whereas when I think of humans, for instance, okay, here's my sort of favorite coffee cup that I use almost every day, and I have no idea how tall it is. Sort of in, like, okay, I can tell you it may be less than 1 feet tall, but I don't have very precise metric estimates for all aspects of it. And so sort of a two-part question that, given that I and probably we humans don't have very precise metric estimates, why is it that as researchers we have gravitated to sort of variants of metric representations for objects? And secondly, are there any alternate representations that you think might be feasible which don't have sort of the metric structure to them? And maybe I'll just put Niloy and Yixin on the spot to get us started.
I wonder how much you guys have coordinated this before. Come up with such tricky questions on the spot. I think you come up with an interesting question, of course. It's something that I thought about a few years back in terms of objects, not in terms of measures or distances, but in terms of function, right? And at that point, the function I liked because in graphics, we have quite some established procedure for doing simulation, right? Like rigid body level, fluid level, everything else. But then I hit a glitch that I haven't been yet able to solve, and hopefully you guys have an answer, that these physics simulator assume a perfect knowledge of the world. Right? So even if one polygon is missing in the wrong place, everything can fall apart, right? And into here. So I think if we can come up with physical model, really physics guided, that can learn directly from raw video, so it learns an implicit model, then I think we can probably revisit this function block. To me, I agree what you mentioned, that object is, if it serves a purpose, some function, right? Let's say, not get deeper question in purpose of life, but purpose of a coffee mug is more understandable and workable. So I think if we can have a block where we can learn from imprecise knowledge, say from video, right? That's an observation that'll be good. Let's ignore frame rate issues. Then one can revisit some of the questions in terms of functionality, for example. And same also applies. We also looked a lot in stability of objects, like if it's a pile or falls apart, etc. But then it's again links to the question, when are parts joined or not, because these are often hidden and we implicitly assume things to be glued versus not. And when we know, if simple things like if I lift a bottle, I'm sure everyone keeps coming across this. I think it's full, but it's empty. I suddenly do the wrong interaction. So our mental models are also tuned because we look at it. I don't measure, I just imagine like this is the reaction force or the interaction we would need. So I think we're still missing that component. We can learn physics directly from data, and if we can replace that from the simulator, that might be an avenue forward. That would be my part of the answer.
Okay.
Yeah.
I
yeah,
have
Yixin.
Quick comment on that. So regarding the interaction, the human interacting with the object or human interacting in the scene in general, there is a funny phenomenon that we seem to represent our interaction from a human-centric perspective, meaning that even though we have never seen how we interact with a normal scene or normal object in a particular way, right? Because when we interact, we are not seeing ourselves from the mirror or from a third person view, right? We are just interacting by ourselves. But we have no problem recognizing this interaction if this interaction were captured by a Kinect and replay from a third person view. So the human has no problem choosing yourself among all the other people, right, doing the same action. So we seem to have a very good representation during the interaction. The problem is we don't know how we did it. So that we can build an AI to do this. But in fact, human is remarkable. There are tons of research on this particular topic, studying how human, this remarkable behavior to accomplish very, very complex tasks. Just a very small comment. Yeah.
I'd also like to briefly jump in on that topic, because I think, like when I think about object representations and like machine learning architectures, then I mostly these days think about effectively just a set of latent variables, and it doesn't really matter what they precisely encode. Like if they have the capability to encode like or to bind to a particular object in the input, then that's kind of success for like object discovery. But I guess whether they encode a particular kind of explicit size of an object or more like semantic features or weight, it really depends on the downstream task with which they're kind of discovered and trained. And I think we don't necessarily need new inventions in terms of how the representation precisely works. I think like set-based vector representations probably can't get us very far. But I think the main problem really lies in like the kind of downstream task of like how do we train those representations so that they actually encode things like expected weight, or like with this example with lifting the bottle. This should be something that should emerge just based on some downstream task with a very simple representation.
So maybe to put it in a slightly controversial way, is it correct to say this is more of an end-to-end framework answer where we are saying, okay, we don't want to impose any structure that will emerge as long as these representations are used in the right context, and we don't need to enforce or even care about metric properties to begin with in the representation?
Maybe I want to touch on something Thomas mentioned. I think whenever I try to do some task and I think slowly, we may not have this robotic view of the world, right? We may not know, like when I lift a bottle, I may not know internally everything I need to do. But what we are very good at, it seems like, I'm not from psychology or who have studied these phenomena, that we are very good at correction, which is something we are not good in long-term learning right now. So once I know like the bottle is empty, I'm lifting its part very quickly. Before I even register it, my muscles have registered it and given the updated signals. So I think this is something very critical, how to quickly understand and work with it. And maybe that gives an answer to your point, Shubham, that that if we are working in gradients, it's a bit like score matching. We don't need to have metrics to absolute ones. We need to do plus and minus, and that can get us a long way if we have a very good correction mechanism and control theory that doesn't result in ringing and other artifacts. So maybe there is something to think about in that direction.
I'd also like to, oh, sorry.
No, go ahead.
I just want to throw an idea out there. I've always thought humans are just bags of heuristics, essentially. So I really like, Shubham, your analogy with the coffee cup. We don't know how tall it is, or maybe as a human, maybe it's, I don't know, a foot tall, but I always wondered, are there ways we can also train machines to basically learn heuristics, or represent an object as a set of heuristics? So from a robotic perspective, you know, as long as I go close enough to the water bottle and squeeze my hand, that's probably enough to grasp that water bottle, right? I have no clue how to train these things, but this is a type of representation that I think could be interesting for object representations. And I think my favorite example of this is Sergey Levin in his talks has this like great analogy of a baseball player catching a baseball, and when you look at the baseball from the baseball player's point of view, you're basically trying to kind of heuristically put the ball in a certain run so that the ball is kind of somewhere in your frame of reference, and you just keep running, and as you keep it there, you can eventually catch it or something like that. I think it's a great analogy for, you know, humans potentially being just bags of heuristics, and it would be really interesting to see machines being trained or object representations being learned in a similar fashion.
If I may, I think that was a fantastic question. I think what's happening is that we're using things like reconstruction, next step prediction, novel view synthesis as our unsupervised training objective, as the thing that drives the unsupervised representation variable. And we do that in the hope that then the representation will have some magic effect on our downstream task. But we haven't agreed on the downstream task necessarily, or know exactly what that magic effect is that we want on the downstream task performance. And so we're stuck with still measuring some things that pertain to the reconstruction task, that pertain to the novel view synthesis task. And those are metric, because we use like a generative task that is grounded in the physical world, in pixel space, and so on, to drive this. And I think what we need to somehow figure out is, if we don't look at the generative aspect of it, if we don't look at the reconstructions, if we just look at what is it enabling downstream, is that for us a sign that we've learned some object interaction? Because as multiple of you have now pointed out, it's very task dependent. It depends a lot on what we want to accomplish later. And I think objects being more or less a means to an end, we have to figure out how to measure that improvement in generalization capacity that we're hoping for in our downstream tasks somehow.
Yeah, actually with this, yeah, then we have a follow-up question, since as you mentioned that we're now like training mainly based on some reconstruction objective, but on the other side, we can still see some like representation learning methods like contrastive learning, right? So these are learning discriminative features by learning away variations, but still keep the information that can help us to discriminate, for example, like instances. Yet, I agree that there's a major effort in our kind of field that, for example, like nerves and some other representations things like generative. There we have a representation that is to reconstruct the inputs, basically memorizing every piece of information in representation. So kind of like want to ask, what are the benefits of each type of representation methods, either discriminative or generative, and how we can use them together to help them mutually benefit each other towards our goal for intelligence.
I think that's a really great question, and especially in kind of object-centric learning, there has been kind of a pendulum swing a little bit in terms of like reconstruction objectives and contrastive objectives, and some of them, like suddenly the contrastive objectives work better, but then the reconstruction objectives again work better for certain tasks. I think we probably need to view this in a somewhat bigger picture, where when we say contrastive objectives, then very often I think we mean like SimClear style objectives, where you have like a single global vector and you contrast that and you kind of get rid of the entire spatial structure of the scene. But I think where those two come very close is if you still take into account like the spatial structure, like you contrast on, say, the grid representation, where things are still grounded in the kind of spatial symmetries of the space you're operating in, and therefore you can still capture things like position of an object if you need to, because if you just have global contrasting, this kind of information will be very difficult to address, especially if you train data augmentation. And so I think like effectively if you just bring these two together by, say, grounding still everything somehow in like the symmetries of the space we're operating in, and not just abstracting everything away into like a single global vector, then those two objectives don't become like so different anymore. Like you basically pixel reconstruction is like grounded in like the physical space, and then these contrastive objectives, if they take into account the symmetries and are not just invariant to translation, for example, but also equivariant, for example, to translation, then you can potentially bridge this gap.
Maybe it's something that has been bothering me the last few months, and hopefully some of you have also observed this. Like with this recent sort of success of language and image pairs, right? This is like this is quite humbling to see. Like with just that, it already learns some objectness. It's not a language only. There is an image pair, as you said, with the contrastive loss. But just with that, with such poor quality pairing, I would say it's keyword based, right? And from that, if there's enough data, it seems networks can denoise this and learn some objectiveness or objectness that correlates with our internal models of objectness. So we can use that now as gradients for extracting, or as a loss, whether it's an image loss or getting out a 3D structure or changing sort of attributes of objects. I don't know where it places us in terms of, it seems like we understand less of it, at least as I would have thought before. Like it learns like deep verbs that we thought were very deep to abstract, but it seems it's doing something. And probably, I don't know what it is doing. And I think if you guys have answered, would love to hear your thoughts on that.
I have thoughts on both, unless someone else is eager to speak. Yeah, okay. So maybe first, the contrastive losses. So far, I've been disappointed by contrastive losses. I really want them to work, because Also for the problems that that you alluded to with the coffee cup, but also for things like planning. If I plan to make a trip to a conference, I make some predictions about my taxi arriving at the airport in time and then being able to catch a flight. I have no idea what that will look like in pixel space. I have no idea. I cannot make a prediction that would be good in an MSE, in a mean squared error case, but still I can use those predictions to like come up with a policy and book the right things and make a trip to a conference. And I had been hoping that contrastive losses would allow us to learn abstract concepts without having to be able to ground them directly in pixel space. But as Thomas has also pointed out, the contrastive things that I've seen working often discard the spatial structure, they discard the object separation. And that is not very satisfactory to me. I hope we can figure this out and make it work. I still haven't given up on them, but they've proven somewhat difficult to work with. And then on the second point about DALI and Imagen and these other image generation networks, I'm fascinated. I would have never guessed that we could like get to this point so quickly. But it is still interesting that these models fail very predictably in certain ways. So while it seems to be pretty easy somehow to figure out what avocado-ness is, and combining it with a chair seems to be a rather easy learning problem, to my great surprise. Doing something like an avocado chair, a strawberry chair, and a banana chair is suddenly very difficult. Like as soon as we go into like asking for multiple things at the same time, the models make mistakes. They make binding errors. They cannot count. They can sometimes count, but they can't generalize this reliably. They can make individual things, but they have a hard time handling the compositionality. And I think that goes at the core of what I feel is still missing. There's definitely aspects of this already working surprisingly well, but there's still aspects of this that are failing. And I would love to try and understand better what separates one from the other.
So actually, maybe the point of compositionality gives me a segue into a slightly broader question that I always wanted to ask, which is, so when we sit down and make a list of, properties of representations and scenarios you'd want them to be able to handle, things like compositionality come up, or for me, even things like, if I'm thinking of a piece of bread, then, if I'm a mover, I'm just interested in packing it, and I think of it as a rigid object. If I'm someone who makes sandwiches, I want to understand that I can slice it and it breaks apart, and and don't know if there's a good word for it, but deformation and sliceability, etc. And of course, things like compositionality. So I was curious on each of your thoughts, maybe sort of putting Chris on the spot just arbitrarily to begin with, on what computational representations do you think might have these sort of list of nice properties that we want from them? For instance, if I say that, okay, I want a representation that can be deformable, can be sliceable, can be compositional, while still having some structure, possibly, what would it look like in code if I want my grad student to think of, some answers along those lines? What should I ask them to think about?
Again, very, very difficult question here.
I'm just hoping I get all the answers from this panel, and then
yeah. So my immediate thoughts on this are not really an answer per se, but maybe a pointing to something else that I believe is lacking in current advances in machine learning, which is, I think in order to have representations that can be compositional and can be operated on, it makes sense that we also have these operators. Like, what does it mean to slice? If we know what it means to slice and we have some fixed operator for that, right? Perhaps that can constrain the representation, and so if we have that fixed form, but at the moment, sometimes we try and learn both forms. There are some papers that try to do some kind of latent space algebra or something like that, treating objects as a latent vector, and you apply some matrix or something like that, a linear transform in a latent space. So you're learning kind of both at the same time, which is very ambiguous. But this is, I would imagine that, in the next couple of decades or something like that, eventually these operators will become causal mechanisms. And at this point, we're far from the question, I think, but it is, I think, one of the big things that will happen in machine learning AI in the, I don't know what near future, but when causal machine learning becomes a bigger breakthrough, right? We have much more data efficient things or data efficient learning paradigms. And when we have these, I think it might make more sense what the object representation might be in the context of a causal operator. When I slice this piece of meat, right? Slicing has a fixed operation, which then potentially constrains the object representation. No idea what that's going to look like, but that's kind of my hope for whenever that becomes big.
So I kind of like to attempt to answer this question of what I think would be the right kind of representation, and maybe see if you can challenge that that answer. I think all we need is effectively a set of high-dimensional vectors, and there's two reasons for that. So one reason is, so first of all, there's kind of two kinds of compositionality that we often kind of put together in one bucket. One is what I would call kind of semantic compositionality. It's if you have features that are not exchangeable, like a color, like red. You cannot exchange red with blue. They have different meanings, and there cannot be two reds, or size, like these kinds of semantic properties of something. And you can even encode objects in semantic features. If you say object 1 and object 2, and you label them as such, then you can encode them in this non-exchangeable way. And vectors are perfect for that. You can have perfect compositionality on the semantic level with vectors. And so the only thing that's missing in some sense is instance compositionality, which is like you have multiple things of the same kind, or multiple things that separately capture certain semantic features and their relations between them. And effectively, you can address this or represent this effectively using a set of vectors. And so the set elements, they have permutation symmetry, and that captures the kind of compositionality in terms of instance compositionality, and the vectors, they have semantic compositionality. And so I think one problem we've always seen in like the disentanglement literature, for example, they focus solely on semantic compositionality. And also what we see in things like DALI, these models are really good at like semantic compositionality, like avocado chair, but they're really pretty bad at instance compositionality. They can do some aspects of it, but it's very limited. And for DALI, it's not so surprising because it compresses everything into a global vector using a clip model. That cannot really be good for like the instance compositionality. But yeah, I'd like to hear thoughts on that.
Yeah, any panelists want to disagree with the notion that sets of vectors are all we need?
Maybe I'll just to be controversial, I'll disagree with Thomas on this one. So I agree with this idea that with sufficient high dimensional vectors, we can do a lot, right? But for certain things, maybe a bag of words success we have seen in the past says that like a bag of local latent code, if that's encoded in a global latent code, that can be enough of a signature. for one snapshot or instance. I think the hope is this would break down as soon as we start interacting, because then it's not like a snapshot anymore. It's has to be consistent across the interaction, and there maybe the notion of objectness will come up again. But I worry that at like static image level, maybe the network can do cheating in different ways and tries to come up with that something that looks photorealistic, for example, without actually have an objectness that relates to what we would call objectness, right? And so I don't know how to avoid such a possible thing. It would be nice if it's not the case, but I do fear that there is a chance this such degeneracies may happen for the DALI scenario.
I also have a very small comments on this topic. So we are talking about composition, but if the representation can afford proper composition of certain concept, then this particular representation should also afford to break down a bigger concept into a smaller one. For example, I can break down an object, a concept of a particular object, into its object parts. So in that way, I would call this particular representation a very expressive, good representation that is capable of a composition. So not only it can compose to form a more complex or complicated concept, but I think it's also very crucial to think in the opposite direction. It should be able to break down into smaller ones.
Cool. Yeah, so thanks for the nice answers. So yeah, so if I may, since we have just a few minutes left, so quick question, which is related to the topic of our workshop. So yeah, so recently we have seen many works on unsupervised or self-supervised decomposition of the scene, heterocentric representations, and also in our discussions we have seen ideas on how we can incorporate human priors or human hypotheses into the learning process so that the repetition is effective and useful. But on the other hand, we also mentioned embodiment. And also I think that the hypothesis or priors we come up with is also like learned or accumulated through embodiment. So I kind of want to know your ideas on how this embodiment or interaction with the environment can benefit object discovery and object-centric representation learning. And especially will the learning towards interaction provide like new insights on how this general topic representation learning or object discovery can be further improved upon our current stage. I guess it's a like open question because this like area is like much less explored compared to the works in the passive regime.
I think there are a few works on this direction, but I wouldn't say they provide answers, but rather an attempt to explore this direction. Like you said, it's rarely explored. So one possible way is to give an answer to a long debate problem. For example, whether we humans predict physical events unfold, whether we are using learned knowledge or it's innate knowledge. So this is a long-term debate like has been forever, almost 300 years. Like people argue a lot. So I think recent work on intuitive physics, this particular topic, trying to say, okay, maybe humans do not need physics engine in our brain, so we just directly predict. So this is one hypothesis. A lot of work try to demonstrate this potential direction. Another one is to say, okay, this is innate capability. This is through evolution. And if I assume human has an intuitive engine in our brain, meaning that we have a rough simulation of what would happen, I can do a lot of things this AI particular can do a lot of things. So both region or both paradigm has been explored with a lot of evidence and results supporting both parties. But I'm not sure which one is correct. I would say it's too early to say who is correct at this stage, but I can see that people are using this kind of interaction as a tool to test long-term debate, to answer a few fundamental scientific questions. So that's my takeaway along this direction.
One thing I would just like to bring up to also answer this question a bit is, in the robotics communities, there has been some level of study into, for example, picking next best views in order to better observe an object. And I think what that is really is an example of what types of directions open up once we start considering the dimension of interaction, right? Where we don't just have a passive video, but we can choose how to manipulate the objects of interest in order to achieve the goals that we want. So yeah, so the best example I can think of at the moment is, an information gain problem where, you want to understand a 3D model of an object that you currently have grasped in a robot hand. Where do I turn this and capture the next photo of this object in order to best understand the 3D model of this object? And so I think one of the biggest things that interaction will, or studying interaction allows for, is to open up these this entire dimension of problems, which gives us more tools we can use or research to help solve discovery of objects.
I agree with Chris, and I also want to refer to something that you brought up earlier, which is causality. I do think causality will play an important role as like an important relation between objects, an important application for the compositionality. And for causality, we know that being able to do interventions can be extremely informative to try and like break down some of the correlations that otherwise might be spurious in the data. And if we don't have enough data, then we might erroneously conclude that this is a signal. But if we're able to intervene and actually do something, we can collect very targeted information to really figure out what the causal network, what the causal structure is. And I think that has huge potential.
We'll say something because we're coming towards the end of the discussion. Let's take a task that I think we are doing all the time. Say, let's say I want to pick up a cup from the kitchen sink and it's not very clean, so there's a pile of cups, and I want to pick it up and place it on a saucer, right? Now, if I describe this, everyone understands what needs to be done, right? But except for the machine, because we need to know the notion of objects. We have to do segmentation, we have to do pose prediction, and we have to do what interaction, what control mechanism we need, how to estimate the weight so that I don't break the cup, and I do all these things. The reason we have made incredible progress in the last years in vision is managed to very effectively break the problem into much smaller tasks like segmentation tasks, depth prediction tasks, 6D OF estimation, etc. Establish benchmarks and people can solve them in isolation. The next task is really, if we go all the way, we just have to solve the full task, right? And maybe we don't, as humans, perform all these in the same sequence or the same set of decomposition in the problem. But in certain ways, we might have made a lot of progress, but in certain ways, we are still far from like solving in cluttered situation where we don't have in a prescribed position, I think. So yeah, I don't know how to make the breakthrough here. I wish I knew. It seems like that in the end we do the full thing, and that's why without all the metrics and all the knowledge we can still function in our day-to-day work. but it's might be a challenge to convert that into an algorithm in immediate years.
Yeah, thanks all the panelists for the nice discussion and inspiring thoughts. Since we're almost out of time, let's now have a brief summary and conclude our workshop. So since the physical scene is composed of objects, and its state is determined by the collection of the state of all constituent objects. Recently, we have seen an increasing interest in developing object-centric representations, and especially unsupervised or self-supervised techniques for learning them. And the high-level points we have discussed are how to define and discover objects or parts, and what could be the right format of object-centric representation, and how they can be used for downstream tasks. However, how interaction and object-centric representation learning can mutually benefit each other is less explored. Yet we can imagine that there could be tons of opportunities at the interface. And this connects back to the theme of our workshop, where visual object-oriented learning meets interaction. We hope that our workshop can serve as a field to give an overview of the recent developments, and more importantly, for the ideas to flourish by taking inputs from our world experts. And with this, let's thank all the panelists and the speakers again. And thank you everyone for your interest and time. And hope you all have a great ECCV this year. Yeah, thanks all.
Thank you.
Yeah, thanks again, everyone, for taking the time. It was a really fun discussion and I learned a lot.
Thanks.
Thank you.
Thanks.
Thank you.
Thanks for the excellent
Bye-bye.
questions. Thank you.
Bye-bye.
Thanks, Yanchao.
Yeah, thanks, Shubham.